Okay, so welcome to this lecture. My name is Filip. I work at LF0. I work on applications layer, ZK stuff. So we daily work with ink, or maybe not daily, but at least weekly. Microphone's not working? No. That better? Okay. So this lecture is a bit experimental. I've shown this material before, but once I heard that we're gonna be almost the entire day till 5 or 6 o'clock, I kind of panicked. So I have too much material. We'll see how that goes. But we go broadly, but at places when it's necessary, we also go kind of deep into ink. So I highly recommend you ask questions immediately that when something springs into your mind. Do not wait. Do not wait until later, because I'm going to forget what I was talking about. You're going to forget what you wanted to ask. So please don't hesitate to stop me and ask questions. There's a lot of examples, like code samples we're going to see. You have to keep in mind that these are just not production code, but examples for the purpose of this lecture. So they are not built to scale, nor painted. Some complexities omitted. And the lecture, I try to keep them like practical, hence the title. So it's like with your regular blue-collar developer in mind. Oh, question. You think it's better?
Yeah.
Does this have gain? Does this have gain or? Okay. So you have seen EVM. You had an EVM lecture. So here's like a slide that compares ink to Solidity. Solidity is definitely the lingua franca of smart contracts. I want to quickly focus on a couple of rows in that table. So first row, Solidity is compiled to the EVM bytecode, and it executes on the Ethereum virtual machine. Ink, we kind of say here that it's any Wasm VM. In practice, it's bound pretty closely to the platform it runs on, so that's Substrate and smart contracts palette of Substrate. Language, Solidity is a standalone language purposely built for EVM. Ink uses Rust. In fact, it's a subset of Rust. It's a DSL written. It's just a bunch of macros, to be honest. And it compiles to Wasm. Some facts of maybe smaller importance is that you can have multiple constructors in ink. This can come in handy. While in Solidity you can have a single. And tooling is probably what's going to be interesting. So if you're thinking about building a product, you have to take that into account. How the whole framework, how mature it is, how much tooling there is, compilers, profilers, all that good stuff. And it's not that bad, actually. It's better than it used to be a year or 2 years ago. And you can also think of ink as a strong contender just because everything that compiles to Wasm, immediately you can use it in your ink projects. Wasm VM uses variable storage. Well, Solidity uses 256 bits, and in practice that means that everything less than 32 bytes is going to be prefixed with all zeros. And that makes Solidity VM much slower than ink. So that's something to take into account. Yeah. Unfortunately, from what I heard, you haven't covered Substrate just yet in the lectures. Well, I'm just gonna quickly go over a few slides that explain where does ink live. So Substrate is this framework for developing customized blockchains, and you kind of build these blockchains from different blocks. So blockchains is built from layers, and these pallets or these building blocks more or less target these layers. And one of these pallets is the smart contracts palette, and this is where ink lives. So this palette gives you instrumentation. It has the Wasm execution engine. It does the gas metering for you. And in fact, you can execute everything that compiles to Wasm. So you can take ink, but there's other languages. There's a compiler that does Solidity to Wasm bytecode, Solang. There's Ask. There's probably some other projects that I don't even know about. But that gives you some leeway, right? This is going to be probably, we're going to come back to that later because we have, at the end of the lecture, we have a small practical session. At the end of it, you're going to, hopefully you're going to be able to take a very simple contract, compile it, and deploy it. But there's a bunch of tooling that you need. Obviously you need Rust, but for the moment it's the nightly Rust because we use a few unstable Rust features, but that's about to change soon. You need Wasm target and you need a Wasm compiler. There's also, we're gonna see this to come back over and over again. It's kind of a command line tool for both compiling, interacting with the contracts, querying them, issuing state-changing mutations, basically transacting with it. So, who's familiar with Rust? Have you even touched it? Okay, so quite a few people. So this is gonna feel pretty familiar. Once you cargo contract can also build a template, starting template for a smart contract. So this is going to feel pretty similar to any other Rust project you might build. It's going to generate a cargo toml file and lib.rs file where the smart contract code lives in. And here's an example. You have ink, here we target 4.3 version. You have the scale codec, we're gonna come back to that later, we're gonna talk about it. And here's a question for you. Why is the standard library not included by default in these dependencies here? Who knows? Yeah? Can you get the microphone to the gentleman? In the back.
Yeah, Mauricio. So because the ink is compiled to Wasm.
There you go, perfectly, yeah. Contracts are compiled to Wasm, so the execution is sandbox. You have no I/O, no networking, no system interfaces, hence no standard library. So here's an example of a very, very simple smart contract written in ink. What it does, it holds a single bit in its memory and it initializes in a constructor, it initializes to some default value that you pass to it. To some value that you pass to it. It has a default constructor that's gonna use the default of a Boolean type. You have a mutation that flips that bit, and you have a getter to retrieve that, to query the contract about its state. All of the contract code is grouped into a module. It's just a convenience. It's easier for the macros to parse a module other than some uncontained code. There's in fact a lot of complexity hidden behind these macros, but you're gonna see the structure, you're gonna see it over and over again. You have a struct, which is basically what goes into the storage, what the contract holds. You have a constructor, you're gonna have some mutations, you're gonna have some queries. A mutation, you can recognize it from a query type of message. because it takes a mutable reference to self, so you can change the state. And getter is like a get semantics, so it takes an immutable reference. You can also have events, obviously, error handling, but we're gonna see that moving on. So here's how you would compile a smart contract code. And it produces some output. So there's basically these three things here. One is a Wasm bytecode. That's basically the blob. Once you upload it to the chain, it just lives under some key. This is the ABI, basically, how you know it from, for example, Solidity development. And this is a file that contains the definition of events, storage, transactions. And it goes back to the fact that this Wasm and scale encoding, they don't carry the schema with them. So you need to be able to decode from something. So it carries that information that other applications that would talk to your smart contract, they needed to decode the events, to know the arguments to the transactions, etc. And this file is just a concatenation of the two. So here's how you would use a cargo construct to instantiate the flipper that we've just seen before. And here's like an interesting song and dance, might I say. So we're seeing two events, right? There's one event for storing the contract, and it carries a code hash, and another event that says instantiated. Deployer is just whoever called that transaction, and we get an address of the contract. When you might be wondering, why is that? Why are we seeing two events? And this is because smart contracts palette introduced an interesting optimization. So unlike in Ethereum, where an instance and a code of a smart contract, they live in the same place, you deploy the smart contract code, so this Wasm blob just once, and every time you instantiate, so every time you call a constructor, it creates a different place in storage for it that points to the code. So it's like it's very interesting because it's like a huge storage space saver, and storage is very expensive on a blockchain. So this allows you to think about, for example, ERC20 tokens, how many countless millions of shitcoins it created. And basically for every one of them, it occupies storage that all the nodes need to keep. This would mean that you only store a pointer for each one of those. You store it once and you instantiate it multiple times. Yeah? Question? Can we get a mic?
Can you just repeat the last part again? Like, so basically, you're saying that the constructor is only called. So for every time the constructor is called, what happens and how is it different than Ethereum?
Okay. So it's basically this. This is in fact two transactions on a chain, right? Just because cargo contract is smart enough to check whether the hash of your code is or is not on the chain. So it wasn't in that case. That's why created a storage space on a chain, and it put the Wasm block. It's basically like it stored there these bytes. And then in the second transaction, so this one, it called the constructor. In that case, even explicitly says it called the default constructor, and that created an instance. So that created this contract occupies some storage, so it has this 1 bit in memory. So it created like in a palette, there's like a tree for the storage. We're gonna come back to that later, how that storage looks like, in fact, how it's encoded, etc. But basically, it created one key over there, and it stored the instance with the storage initiated to whatever the default value is.
Can you maybe like relate between different cargo commands there to the
Between different?
Sorry?
Between different
cargo commands, the parts, like, so we have cargo contract,
Yeah.
instantiate, and then it tells it this is the constructor, which is the default, right? And then it gives it an address, I guess.
No, this is just so the Suri. This is just a private key that you use to sign the transaction.
Okay, to sign a transaction.
And this just says
Skip confirm.
yeah, this is a CLI tool, so do not wait for a yes, execute immediately, and skip a dry run.
And then how does this relate to the different functions in the code, in the contract, like the?
So the only thing that relates this to the code that you've seen is that the constructor, because that's the only thing that you call. You call the default constructor. You could call a new constructor, and then you would have to pass it a value. That's it.
So basically, this the new function, right? Or
You called this one the default. You could have called new, but then you would have to pass it
I see.
because it allows you to define multiple
And
constructors.
then that creates a instance of the contract. Like
It creates the instance of the contract. It initializes the storage. It stores all that on chain, and in addition to that storage, it stores a pointer to the actual code.
Okay.
So this address, it has an address, right? And for this address, it knows that the code of the contract is stored there. And that's the actual key under which it lives in the palette storage.
Mike?
I can. I'll repeat the question if.
Hello? Okay. Sorry. This default constructor can be invoked by anyone. It's okay.
It's a good question, actually. Yeah. Once the code is stored on chain, unless in the constructor there is some logic that would revert the transaction, anybody can call that. That's a good question. Yes.
And this, sorry, it just create a new instance in the blockchain, like a new deployment of the object, Flipper.
It's not a new deployment. It's just it just creates an instance. So it basically initializes the storage of that contract at that
okay.
point. That's all it does.
Okay, thanks.
I have a question here. So just to see if I get right, you split storage from the bytecode, right? And what if you implement a new function? Let's get an example of a token. On EVMs, we have like the transfer from, and there is a function like before transfer from where you can implement anything. If I implement something different, then this will generate a different bytecode. Then I will, in this case, if I, for example, I want to deploy a token that implements a very specific function, I can look in some kind of library to see, oh, someone already did that, here's the bytecode for that, instead of deploying again?
That's another good question. Let me come back to that when we talk about upgradability. But it's a very good question. But I have to move on, I gotta say. I didn't expect so early there are many questions. But hopefully, we have a lot of material to cover. So, but I'm gonna be here till Wednesday. Okay, querying. This is how you would query. So what we call the get message on that contract that we've seen before, the flipper. Actually, who knows what's gonna return? Tips that the default constructor was called. Who knows? Yeah, yeah, exactly. Yeah, the return is false because that's the default of a Boolean variable. This is a mutation. That's how you'd call the mutation. So we just flip a bit. And we get it again. We get a flipped bit. No surprises there. So you've seen the Cargo contract key. There's also a user interface tool called Contracts UI that allows you to do pretty much the same things only from your browser, which might be convenient for moving fast. Here's how you deploy and instantiate Flipper. You can call a transaction even if you compile it with these debug messages. It shows you gas metering of the Wasm instructions, which could be useful, right? This is a dry run, right? So we have not executed, we have kind of simulated the execution, but it would be successful if we did. This is useful for like profiling, debugging, querying, same thing. Okay, so this is, we're gonna dissect a little bit more what contract code is built like. So we've already went over that, but there's basically no limit on the number of constructors. We have free constructors, right? We could have constructors calling other constructors, like we can, each one of these, that's how you would actually recognize a constructor. It returns an instance of a storage. So in that case, the storage has a single bit in it. Since recent version of Ink, you can return a result. So you can have a constructors that fall, and it will be, it doesn't just panic. Panics are kind of hard to debug. But results are nice enough because you can give it, it's your own semantics basically for what's fallible, what it's going to return it, so it makes it a little easier. So in that case, we have a constructor which might result in a success or a failure, depending on some function that can fail in some circumstances. This is your typical query. So a reference to self, unmutable reference, returns a type, and you read that type from storage in that case. You could have pure functions as well, there's no problem, right? You could have a message that like adds two numbers, returns a result, so reading nothing from the storage, there's nothing stopping you from doing that. It's not mutable here. It's not mutable because it's not a, yeah. If it was mutable, you would have to transact with it, you would have to pay gas. Here's a mutable one, right? So it takes a mutable reference to self. There's also, so this macro that marks a transaction, if you want it to accept funds, you have to mark it explicitly as payable. And we'll see it coming over and over again, like Ink is a lot more explicit than Solidity. Everything like the visibility, these type of macro constructs, they're explicit. Oh, we have a question?
Mike?
Just a quick question, just to make sure I'm understanding here. Going off of what he said, more or less. In order to have a immutable self, you had to make the you had to use the payable macro up there, more or less, or could you just have immutable as is, more or less, for self?
Come again? What type of macro?
Oh, the payable.
No. Payable just means that it accepts funds, and it was introduced because you might by mistake send funds to some contract that was not supposed to accept funds, and in case it type inc, that means it just creates, like, generates code that checks for that and would reject the transaction so that your funds are not lost.
Oh, okay. So immutable self is just independent of.
Yeah,
payable,
completely
basically.
two different things. Exactly.
Okay.
Exactly.
Just making sure. Thank you.
Yeah. And in fact, once it's been payable, there's always this unf object, and you can read all types of like runtime environment things. So for example, caller is gonna be whatever address called the message, like a user, another smart contract, and the funds. So this is gonna be the native fund of the chain. Is you can read that using this transferred value function. So this is just how you flushing. When we talk about the storage, this is gonna be a little bit clearer. But here's how you would flush state, for example, basically make a write. And if a message if it's a mutation, right, then you are metered gas both for the writes and for the reads. Same as with EVM, actually. Whilst queries, so like we've seen before, this getter, you're not paying anything. It does no gas metering in that case, which allows you to play like some games optimizations. Error handling. So here's where we start getting dividends on the fact that we use Rust. So for error handling, Inc uses idiomatic Rust results. And this allows you to return an error variant. So the way you do it in Inc is you define an enum with different variants. And this is like anything goes. Whatever semantics makes sense for your smart contract, this is supposed to be human readable, because this is how you're gonna see what went wrong or how you handled different transactions, whatever makes sense in the context of whatever you're writing, right? And here's an example. So we have a mutation that returns a result with like no type. A result is either a success or one of the variants of the enum. Here's the result. So this is just to reduce a boilerplate. So I'll define it as the core result with some type, generic type T, and a variant of my enum error. And just because it's Rust, so the compiler will make sure that you handle every possible place where this can fail. This makes it actually quite pleasant compared to Solidity. So here's a question for you. Yeah, we have the same flipper, but this type, depending on whether it's an odd or even block number, it panics or not. Panicking is, a side note, for the call stack, panicking is the same as unwinding on a error variant of the result. It just, panic will just revert the call stack, and a result will basically tell you what actually went wrong. it will give you a human readable error code. So basically, there's a question for you: what's the state of this contract? The transaction is called in an out block. And by state, I mean, was this bit flipped or not?
Hello. Hey. So according to what you just said, where the panic rewinds the stack, so that would mean, I think, that the mutation didn't happen.
Yeah, of course, obviously. So this, in this case, indeed, it panicked. So it reverts the entire transaction on the call stack. So that even if the mutation was here, it would never reach it. It's the same as mutating it here and panicking. Everything that was on the call stack. From the moment that we called this transaction, it just unwinded. Question?
Hi. So if the panic is in a smart contract that is invoked from a parent smart contract, would it also roll back the parent smart contract?
So that's exactly what we're going to talk about in this slide.
Thank you.
You just asked the question now, so you can actually answer it if you already have the mic. No, I'm joking. But here's if you're asking, that means you probably don't know. But here's an example of to your point. We have a cross-contract call. It's just a piece of code from I think it's like some contract that counts. This could be like a wrap around ERC20 that just counts how many times a successful transfer has been made, and it takes a reference to another smart contract that's like basically follows the PSP22 interface. PSP22 is basically like think ERC20, and it makes a cross-contract call to it. So it calls this transfer to function to transfer some amount to this account and passes some empty data at the end of it. So here's the question, right? What is the state if this transfer failed, right? So this whole, it can fail, right? It can return a success or an error variant.
Yeah, so we're saying if the transfer failed, right? So because we're saying if it's okay, then do like increment the counter. If it's not okay, then return okay.
Yeah.
So there won't be a mutation here, but it will return okay.
Yeah, that's correct. We handled it, but we didn't unwind the stack. So it's just basically a no-op in that case if that failed. Yeah. So this gives you like options, right? You don't have to. It doesn't mean just because a cross contract failed. It's whatever you did with it. And same other like you could do some arithmetic, have a division by 0, and if you handle that, it's handled, right? However you want to handle it. Do you unwind or do you just move on? Up to you. Mike?
So I can just choose to unwind in this case as well, right? If I call a contract that fails, and like whatever I do can be unwind. Okay.
This is just a shorthand, right? So you could match. This is also fallable. So a transfer returns a result, which is a success or some other enum that defines error that makes sense in the context of a PSP22 token. And in this case, like, was this successful? Yes, okay, execute that byte of code, but you could have an else, you could pattern match on that.
And the best practice is to, like, if I'm calling other contracts, is to have a transformer for their errors to my error or something like that?
Yeah. You should probably do that. Rust has like a trait for it that you could implement. It's called a from trait. Yeah, and you could indeed it basically once you implement the trait, you would return some variant. Usually, you would just wrap that other. It would be like an enum variant that wraps this other error, not to lose context, because then all these tools like cargo contract or the CLI tools, these browser tools, they would just show you the variant, so you don't lose context if you. But you can do whatever, right? It's up to you. Any more questions?
I have a question.
Oh, okay.
Not related to this, but like the storage in the previous slide. Yeah, there's a top line, public transfer count. So generally, can we have multiple storage, or we have to deal with only one storage?
Multiple. There's one storage.
Only one storage.
One storage per contract. But I mean, you could. The storage in this case has one field, but it could have.
Yeah.
We're gonna talk about storage like in more detail. In fact, it gives you some. I'm just gonna say right now that it gives you some leeway in how you structure your storage. So whether you store all the things in one place or whether you kind of spread them around, and that because in when you transact, so when you do gas metered transaction, state mutating transactions, you are metered for reading, but also for decoding things. So once you read something from the storage, you also still need to decode it into the actual types, right? You need to know whether it's an integer, what type of integer that is it a string, whatever is the vector. So you are metered for it. So it kind of makes sense from the gas cost perspective to limit the things. If you do not work, like if you discard a field, then why read it? Why pay for decoding it, right?
Got it. Thank you.
In the end, can we get a? Oh, you have
I got
a
a
mic.
mic.
Smart guy. All right.
Yep. So to me, it seems like, Inc. and I guess now for the most part, a lot of the substrate stuff, it's really focused on kind of the traditional EVM account model, where essentially smart contracts hold both the logic and the state within it. Is there any work for allowing Inc./Wasm to support different account models like the one in Solana, where the state is stored separately from the contract itself?
Well, I mean, in this case, state is stored apart from the.
Yes. Is there any work outside of that to allow Inc. to support these other kind of account models that are out there?
So this is Inc. or actually Substrate itself.
Yeah.
It's abstracted over the account model. There's just a type, or actually a trait. This is very vague about what it is. So you can do whatever. You could even have an account model where you map, where you actually have one account, so like some higher notion of an account, and you could have this SS58 type of accounts a subset uses and an EVM. So you could have, for example, both an EVM machine and a Wasm machine in the same chain. But Inc. is kind of oblivious to that.
Right.
It just works. It just knows about an account ID, but it makes no assumptions about what that is.
Right. I have some ideas now. We'll have to chat with you later on this.
Sure.
Thanks.
Excuse me. So in this online 14, if you don't use is okay and if block, just the transfer line, then, and in the subcontract, if you don't throw an error and it's a panic, then does this crash too?
You mean, yeah, I mean, if this panicked, if it's not handled, I mean,
Like is okay. Like what I'm trying to gather is it entrapping the stack trace just because we wrote is okay in an if block? And is the subsequent throwing an error as a result or a panic? Like
This is handled by the type system, right? So if this does not return a result, then this cannot be okay or an error. This is this you just get because you know the definition of the transfer, and you know that it returns a result.
Yeah.
But if it panicked, it would trap your whole contract, right?
So if the subsequent contract panics, then this will crash.
This will, I mean, crash. It would unwind basically.
Right. So
It's,
yeah, go ahead. It was the confusion. Like what I was thinking earlier when I asked the question was, if in case your previous example had explicitly mentioned panic, which is like go kill somebody, right? So that irrespective of the fact if we are tackling or not, this will unwind, right?
you mean if this panics?
Yeah. If
Yeah, this would unwind. I mean,
right, like
yeah.
if transfer internally has panic, like let's say.
Panic is the same as returning an error variant, basically, internally. It's just for you as a developer. It's a convenience for humans.
Yeah. Okay. So in this case, if it's not saying is okay, it's still fine, right? No? Like
If this
what I'm-
panicked before reaching the instruction, then so I mean, if we're talking about
let's say let's remove the transfer, and if we put the previous code in here, right, like the previous contract code that checks for if it's even or odd, and then it calls for panic,
yeah,
right? What would happen then if it's not, if this is called directly inside there without an if block?
panic, that's it. That stops the execution and it unwinds the whole stack trace from the
Even the other
moment where
one,
the
right?
transaction started.
Even the other one.
Yeah.
Okay, thanks.
Okay. So this is defining shared behavior. This is this ubiquitous PSP22 thing, ERC20 trait. So basically a definition. So every other contract that adheres to that definition, we can think of them as PSP22. Solidly has a very similar concept. And you can share that definition with other contracts without sharing the underlying logic. So the only thing that's going to know is what type of arguments and what's the return value, the type actually. What's the type of the return? And this, but basically that's how you would do a cross-contract call. Here's an example of that. We're reading a balance of an account. It returns some balance type, which is just an unsigned integer, in fact. And you do that by, so you get all this nice type safety by sharing that definition. Pretty neat. You could do a much lower level contract, cross-contract call without knowing that definition, but it's just much more verbose, but it gives you that possibility as well. We will have an example. Events. So events are in fact super important, just because your contracts rarely live by themselves. There's other like entities, other programs living outside of the chain that listen to them. In Ink, you mark a macro as an event. You can index different fields of that, so that allows you to filter faster on these fields. You can have multiple, I think up to 3 index fields. Question?
Hello? There we go. Okay. So, more or less, as my mentor probably shaking his head in regards to one beat. Anyways, so is this concept more or less similar to that of Solidity, where more or less you're able to emit events after like uh, executing a executing an actual function within the smart contract, more or less?
Yeah, yeah, it's same concept. Yeah.
Oh, okay, cool.
It was.
Thank you.
So these events, they're super important for dApps. It's letting outside world know what's happening inside the contract, but not just that. We're gonna quickly mention what else. Where else can you use events and what for? But basically, in the course of execution, your contract emits these events, and because storage is expensive, and blockchain, you can kind of think of it as a database, but it's kind of a very bad database. So if you want to aggregate data, for example, you'd need to read it, normalize it, store it some off-chain where it's easy to query in whatever form you want. And what happens, events are kind of like storage. You can think of them as storage, but they're more like logs of what happened. And they adhere to the same rules as the rest of the stack trace. Yeah, so here's actually a question. Is this event emitted in the out block or not? Who knows? Who can tell me? You've seen that before. It's the same code, only that we emit an event before panicking or not. Well, it emits an event. It puts that event into log. It's not a storage exactly. It's like a different type of storage, but it puts that into the log. So whenever you replay it, you replay this transaction, it's also re-emitted. It's yeah. Mike?
I think it will be emitted unless we have like a rollback function that can delete it or something, maybe.
Yeah, yeah. In this case, it's emitted. But if it panicked, so if this was an even block, it would be rolled back. Same as all the other storage mutations. And it would be very inconvenient, or actually it would make the events useless if it wasn't the case, right? Because they are like a view into what's happening. But in fact, in the later part of the day, when we talk about MEV, there's examples of the games that people play where they emit events that kind of make things look like they went okay, but they didn't, in fact. But that's for later on.
So, sorry, actually, my question about emit event was because I was confused. If it's writing to an external storage, do we also revert this storage? Or
if it's writing to external storage, you mean other contract? What do you mean by external storage?
Yeah, I'm comparing it with normal, like if it's logging in the machine, it will be maybe writing to a text file, or maybe it will be calling a service or something. So I'm trying to understand.
I mean, there's no I/O. You cannot write to a file from a smart contract.
Okay, see, so this is all in the state, not like.
In fact, the only thing that smart contracts can mutate is their own state.
Okay. Yeah.
I'm simplifying things a bit because there is, again, later in the lectures, Piotr will talk about how you can, in fact, reach outside of the sandbox of smart contracts, but that's for later on. There was another question? Or maybe I'm wrong.
Okay. So what exactly is the difference between emitting and inventing the constructor and here now the message. Is there like a difference?
Are you asking whether you can emit an event in a constructor of a contract?
No, I just want to understand, like, is there a difference between emitting an event in like a constructor and a message? I don't know if I'm making sense.
No, you can, it's perfectly fine. You can emit an event in a constructor, sure.
Is there any viable difference between the two? Like, is there a scenario where you will emit an event in a constructor and another scenario where you emit an event in a message? I don't know if I'm making sense.
Yeah. No, like for all practical reasons, calling a constructor initializes a storage, but then writes to it, and then a message already has storage to work with. So it mutates that state, but this is kind of a different layer. It's like a log. So it's not the same as writing into storage and events. Events are put into a bit of a different place. In fact, if you wanted to replay all the events, not every node might know that. You need something called a full node, so that really has all the past state and can replay it. That gives you the events. So it's actually, if you were like a off-chain indexer, let's say like an Infura node, or a light node, that makes a difference. So you're kind of okay if you lose that state. If you were an indexer, you write it to some relational database, whatever, and you lose that, you can still replay the chain, but it's gonna be costly. It's gonna be slow because you need to do it synchronously, like block by block, transaction by transaction. You can do it. But that's actually why these off-chain indexers even exist, because it's costly to replay all these events.
So just to understand, like you're saying that in any case, if we panic or unwrap whatever in a call basically, the function, then due to the nature of Rust, basically anything that happened before will not happen.
It's not Rust per se. It's more like how.
So the rollback mechanism is basically part of the
palette.
Okay, I see. And then my other question is, like in yesterday's lecture, we had this question about like, look at this Hong Kong whatever Ethereum contract, and there basically it presented the same problem, a similar problem, where like an exploiter can exploit the contract because of exactly the order of verification. So basically, if we verify after a mutation, then that mutation would still happen. So is that the point here, that like in Inc, like we kind of prevent these things that in Ethereum are by default enabled?
You're asking about reentrancy, probably, yeah? So no, there's nothing in Inc, and in fact, we are talking about exploits later on in the lecture. So I hate to keep saying that. It's a good question. But no, in fact, there's nothing in Inc that would protect you from reentrancy.
I don't think I was talking about reentrancy. Actually, there was the specific case of like this verification, like assertion, basically, like fail if this. Maybe it was reentry, but like let's assume that it was. I'm not sure. I don't remember exactly, but I think there was something about like fail after the mutation happened. So yeah, I don't know. Maybe I need to. Maybe yeah, not sure.
It's a little bit more subtle than that. Like you have all these instructions, right? And they kind of happen synchronously, and then the transaction block happens synchronously, blocks happen synchronously, all that. But
it's just a transaction management, basically.
The moment that you have some cross contracts calls, so you reach outside of your contracts, this is where things can get hairy.
Yeah. Okay. Understood. But in the simple case,
In a simple case, if you have a single contract that handles its own state, I'm gonna say, like, as a rule of thumb, it does not matter whether you mutate here before event or after.
But the concept is similar to like a database transaction wrapper.
Well, in a relation database, you're gonna have a schema, right? So, for example, you're gonna have some relational object that has a field, and that field needs to exist before like a car and its driver, and in a database, you're gonna check whether the driver exists before you can insert the car, that type
Whatever,
of thing.
like
In blockchain, I mean, you could build a thing like that, but it's gonna be expensive to check.
I'm not talking about the cross contract thing. I'm just saying that like what Ink does here, generally I guess, is that it provides like this rollback mechanism to roll back due to like after any failures that happen within the same function. So that is kind of similar to transaction management in a database, apart from the cross entity thing, I guess.
Yeah. So it's more like in a relational database, you can put multiple like mutations, and you check whether all of them executed or none of them executed. It's more like that. Like none of these are written. What the hell? None of these are written into the storage. Yeah. Before all of these have been executed, right? So, and because of that, it kind of does not matter, like the order. You could emit the event here, you could emit it there. Sometimes I have a hard time like thinking about any other example other than cross-contract calls where reentrancy, we're going to come back to that, but the reentrancy can generate type of like a recursive type of call, like an evil feedback loop. So that's different. But generally, like, none of this is written in stone unless you have executed all the instructions. And remember how blockchain works. Like every validator out there, he's gonna run every one of these transactions, instruction by instruction, like block by block, every one of them. So you cannot have a situation where one has a true before he emitted the event and the other one has a false after he emitted the event, all that. So in fact, even though they are synchronously executed, so are their writes. So if this is a valid transaction, then like the state change is written. It takes just like a snapshot, executes it, right? Checks whether it makes sense, and it writes it to this blockchain storage, and eventually becomes part of history.
Hi, Sukmit again. Usually in an event system, there are publishers and subscribers, and that's what we know from the theory part of it, right? So in this case, where would be like a subscriber to it, or it's just like logging inside the contract because it's just writing ding, 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 this happened.
It's both, but it's a good way to think about it, in fact, right? Yeah, like, it's like a fan out,
Yeah.
to say.
So it's just logging, right? Like boom, 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 boom.
That's a good way to think about it, yeah.
Okay, thank you.
So here it's a bit of a tricky question. I tried to trick you, but I'm asking about the not block, right? But the condition is reverted, so it does not panic in that case. We kind of talked about it already. But maybe I want to add to that one thing. That events, they emit they are emitted by transactions. As a general rule of thumb, these transactions take place on a blockchain. But exactly what are they useful and why? So you have to think about what happens when a transaction is submitted. When you first submit it, it goes to a mempool. It lives there for a while. Eventually, it's picked up by a miner, validator, whatever block producer. Eventually, it's included in the blockchain. And that means that there can be quite some time, depending on the conditions, the network latency, the type of consensus that we're working with. But basically, all these transactions, they are not going to immediately return a value, right? There's going to be some time passing up. It can be even hours in some cases. So that means that indeed, it's not like an HTTP request where you have you ask a question and you immediately get a reply. It's more like a kind of a WebSocket type of thing where you send something and you subscribe to get an answer. So that's why if you want to kind of real-time display what's the state of a particular smart contract or a set of smart contracts, you need to start working on these events because they give you a window to what's actually happening on a blockchain. But you can, like I said, you can actually cheat because there's nothing, you put whatever you want, like whatever the smart contract developer put into this contract, so you can play these games where you emit events that do not correspond to what's actually in the storage, but it's like a different type of game. So a good example of that is, think of a token, right? So a smart contract that's like an ERC20, BSP22, whatever you want to call it. It generally is a glorified mapping, glorified hash map, where for every account we keep a balance, right? It does not keep track of the history of all the transactions, so who sent whatever to what. Just at the head of the chain, Alice, Bob, Eve, and Charlie, whatever are their balances. That's what you can ask the contract about. You cannot ask like, hey, 3 blocks ago, what was the balance of Alice, right? So enter events. If you were listening and you were like processing these events off chain, you can build some type of view out of those. You put some API over that, GraphQL or whatever, and that allows you to query past historical data. And there are in fact whole projects, right, that made it their sole business to facilitate querying events. So if we're talking about Substrate, there's, for example, Subscript that allows you to query Wasm type of contracts. The graph is like a big one. I think it targets Substrate as well as EVM. And basically, they differ in the thing. The way Subscript is more like they give you an SDK to build your own indexes, host the database, host the process itself, an API. The graph, I think it allows you to define like a schema, and it creates an API over it, so it's like higher level. Subscript gives you a bit more control. Or you can roll out your own. There's nothing stopping you. Whatever floats your boat. And there's one more esoteric use of events, especially in the EVM. This is the current gas cost of writing into the storage, where writing to the logs is orders of, in fact, 4 times cheaper than writing to storage. So events, you can use them as type of cheap storage as an optimization with some work. It's less of a case for substrate chains, which tend to be cheaper, but in some cases might still make sense.
Hello. So, based on that, an event can be read by a smart contract.
Events, no.
Okay.
No, you need to have some sort of chain process that facilitates that. Yeah.
Okay.
Now,
So it's only for outside communication.
I mean, you would have to build, like, generally, the like virtual machine, it does not move. It's not Turing complete, basically. So you cannot have an infinite process that listens to something off chain. And you need some sort of input to move it. The only thing that moves is like blocks, right? It produces blocks. Time goes by.
Thanks.
Okay, so we're actually moving faster than I expected, which is a good thing. I think we're gonna start with the deeper dive right now because we still have half an hour till lunch. So in this part, we're gonna mainly talk about storage, how it's organized, what goes into the storage, how it is organized in there, how it's encoded, how you go about decoding it. So let's dissect it a little bit more. So we started with this very simple contract which had just one Boolean value inside of its storage. Here we have a little bit more convoluted example. So we're going to try to explain what actually does this mean for this storage. So we have 3 fields here, right? We have a single value, but we also have this mapping thing. Should
Yeah, before doing the deep dive about the events, can we have on-chain listeners? So instead of having the indexers that listens and like have their own indexes and databases, can I have a smart contract that is listening to some events to take an action, for example?
no, no, because space in a block is limited, right? So, and actually, while you're building that block, there's other people waiting. So they're not gonna wait forever. And to do what you want, you would need type of like an infinite loop. So it's not possible to build something. You'd have to facilitate it with some off-chain construct.
Yes.
But it's not that hard to build, to be honest. I might add that Substrate has a construct for that, or actually like within the framework, there's something called off-chain workers that would kind of allow you to build something like that. So before we go back to start dissecting the storage, let's talk about scale. Scale is basically a codec. A codec is used for the values that you put into this key value storage, which is the database the database used by both by the pallet contracts and like by Substrate in general. So you have keys of varying length, actually, so not just 32 byte keys, and you have values by them. As easy as that, key value database. And scale is is basically a way of encoding Rust types, in this case, into bytes. It has its, here's like an example. It is not exhaustive example of scale encoding and decoding. But you might have Boolean, right, which is least significant bit of a single byte. So true is 0, false is 1. Unsigned integers, it's just, well, it's just the hex value of that integer. Enums. Enums are a bit more interesting. So you have, enums have this finite number of variants. So the first byte is going to encode which one it is, right? So 0, 0 for the int, or 1 for the Boolean, because this enum can take an integer or a Boolean value. And then the second one encodes the actual data, right? So yeah, who knows what this is? So this is the first variant of the enum, and what's the value? 42. And here is a falsy value in that second case. Tuples, it's just a concatenation of the values, so free and a false. Vectors, so vector on its first least significant byte is going to store the length, and then the concatenation of the items. All the items have the same type. Structs, so that's kind of important. We're going to see why. It does not, structs have names, but that's just, this is compiled away later on. So the name is ignored, but the order matters. We're going to come back why that it's important, but it's basically encoded as a vector structure with different fields in the order. Yep.
2 questions, please. The first about
hold on. Mike?
What do you mean by order matters over here? Only order matters. What does it mean?
Because the order, why does the order matter? Well, basically, because they have different types. In a struct, like all these other constructs, like with an enum, the position defines what the type it is, right? Vector, everything's going to be the same type. If it's like a single value that takes a single, that takes one type, it's like a Boolean value, an unsigned integer. So that's self-explanatory. And here you have nothing else to go by, but the order.
So you mean the order of the variables within the struct type variables, right?
If you switched, right, you wouldn't know how to decode. If you switched integer with a Boolean, right, you wouldn't know whether it's 1 or it's false, for example.
Hello. Hello. One question. Regarding the struct, the X30U64. Okay, I see that it's the 13, but it says is U64 is not expected to be 8 bytes.
Oh, it's yeah, it's omitted.
Ah, okay.
It's the least significant.
Yeah.
One question?
So about the structs, do we need to write the size of the variable beforehand? Like if it's U64, so we write the index and the size? How are we going to know that it takes this like this amount of bytes or so?
Because you always read lists to the most significant. So if there's still something to read, you have, like for the, whenever it's like an outside application, it's going to have this ABI interface to know what the types are and how to decode them.
Okay. And the second question about the true and false.
About?
The Boolean.
Yeah.
Why the choice is that false is 1? I mean,
In most programming languages, like it's false is 0 and true is 1, right? Like, is this something intentional or?
No, most languages it's 0.
False is 0. Like in
Yeah.
C++, you can say that if boolean equals 0, for example, right?
Yeah, I'm not sure. It's just a choice, I guess. Not sure.
Okay. Yeah. Thanks.
Excuse me.
Maybe it's a optimize. No.
Zero is a safe code, so it's like in console terminal it comes out as 0, it means everything went fine.
Yeah, but then again, it's like a choice. Maybe in Solidity, like a 0 is uninitialized. Maybe it was carried over from Solidity. So, for example, addresses, the address which has like a bunch of zeros at the start of it is in fact going to occupy less space in the storage. But it's not the case here because you initialize the storage. There's nothing in the storage, so yeah, I don't know. I'm not going to speculate. I don't know.
I have a question about structs. Usually in computers, like everything has a limit. So is there a limit to actual how size of struct, how big it can be? Or it's not like it can just grow?
You just know, the types, so you know what it occupies.
You know what I'm saying, right? Like struct could grow. So
like in this case, right? You have 1, 2, 3, 4. It's a U64. You keep reading until you fill that buffer.
So if I'm looking at a banking struct, so it could have like 10,000 fields in it, right? Something like that.
There is a limit. Yeah, that's a fact. There is a limit, 16 kilobyte limit, I think, on.
Thanks.
Not sure about the exact. Maybe it's even a configure number, but there is a limit on the buffer for decoding. That's a fact. It cannot go, which would make sense because otherwise, you could. The virtual machine could panic even on a read. Should.
So I just want to ask a question. I checked on the docs substrate, and it says that false is encoding to 0. So I think it's just typo, right?
Oh, yeah, could be.
Because in the tuple example, when we combine 3 and false, it gives us 0. And I wanted to ask a question about.
Yeah, you're right.
So you said that the order is important, and what's your recommendation? Like, should we start with a bigger size first and then reduce it to like?
Why would you start with a bigger size first?
I mean, what's a better practice to allocate the structure, like fields inside the structures? Like,
you mean for a tuple?
No, I mean in the structures.
Yeah.
Like for example, in that case, we used U64 and then boolean, and if we reverse it, it can be like bigger size or less.
Yeah, but why would you?
So it's like doesn't matter like the order.
I mean, it matters for when you're decoding that struct, but why would you put a bigger field first? I don't see a.
So what I meant is in some programming languages, the order matters like on the size. For example, if you put some fields in one particular order, it can be encoded in a less bytes, for example. And if you reverse it, it can be bigger and so on.
You mean like no, it doesn't have. Yeah, it could be an optimization. Yeah, you could do that, but it's not the case here. Not with this encoding. I mean, this is not a. If this was like some embedded environment where you really have to fight about every kilobyte, that yeah, it might bother. But yeah, be honest.
Thank you.
Yeah, but there's a lot of you could compress, it, but it's just not a problem thus far. So no one bothered. You could do it.
one question. Okay. It said that the enum type, the first one goes to variant of the index, but what would happen if like, I know this is probably unrealistic, but what would happen like if the variance just overflow like 256?
You'd have to repeat the question. I didn't.
Oh, sorry.
I got none of it.
Okay. So it said at the enum type, it said that the first byte encodes the variant index.
Yeah.
Okay. So, but what would happen, let's say, for example, the variant index exceed 255? So 1 byte doesn't like, you know.
You'll hit the decoding limit way before you exhaust.
Oh, yeah. Oh, yeah, it's hex, so you can't go over 255. Oh, yeah, this makes sense. Okay.
Questions?
Yeah, I think it might be a typo with the false. I checked the substrate.
Yeah, it's a typo. We already
okay.
Established that, but thanks. Oh, I'll upload I'll change that, upload the text version. Okay, so we are talking about that key value database, how it's used, how the values are stored. And now we're going to talk about how you can occupy the cells of the storage. So there's basically two types of cell occupancy that you have access to, and one variant of the second type. So by default, everything, so like here, you have some root of the storage. Typically that's under a key 0. You have all these values, and by default they're stored under a single cell, which might be something that you want, might be something that's just, it might be not what your contract needs, because it might be needing access to just a subset of those fields. So this is like it matters from the gas cost perspective, which quickly adds up. In fact, you can even have transactions that potentially, under some circumstances, they can exhaust the gas block limit. They can never be executed, in some edge cases. And then, depending on this access pattern, you would want to start spreading things around. So you would want your contract to read only the data that it immediately needs access to. So here's an example of a flipper again. It has the root storage, so it has this Boolean value. In this case, we manually define the key under which this is going to be written to. So this is the state of the storage. Here's the root key, right? And under it, you have the single value Boolean, which is false. Another way of working with storage is to spread things around. So this is mapping. It basically allows you to work directly with that key value storage. So what that means is that every value occupies a single cell in that storage, and the key is whatever the mapping key is, and it can be any type. This could be a struct, like a tuple. This could be a single type, and it points to a value. And why is that important? Because if your message reads from that mapping, then it's gas metered for only decoding this single value that lives under a single key. And not reading the whole map into a memory, which could be huge if you're thinking about like a token type of contract where there can be hundreds of thousands of balances. There are other collections, like you have your hash map, you have your tree map, but they do not in ink, or thus far they do not display that behavior. So they all live under a single cell, in fact. So reading that, you would like kind of decode the whole collection. And mapping is different. Mapping is really a direct way of working with key value database. But there are some caveats for working with mapping. We're gonna go over a few of them. But right now I can even tell you that, for example, it's not possible to iterate by the mapping. It does not, like one cell does not know, does not hold a reference to any other cells. Or even get a count of that. That's impossible. You'd have to store it into some different value. So all of that you need to think about when you're designing the smart contract. And here's another one. So a transfer function takes immutable reference to self, so that means it's transacting, changing the storage. That's whoever called it, right? We read that account's balance. If it's not there, it's 0. And we add whatever value was transferred, we add that to that balance. And the question is, what's wrong here? Why is that a bad idea? Oh, I don't know, you have to battle it out, I guess.
Does the balance not need a mute field?
Come again?
Does the balance not need a MUT field? Like it's just...
Yeah, that's a good... Yeah. Well, I mean, it's not just that it's not mutable, but yeah, that indeed tips you. It's a copy, in fact, or whatever you read from that. So this is like a copy semantics. So you do not get a pointer or even a mutable. You do not get a mutable pointer, not even a pointer to that value. You get an exact copy of this value. So this is not going to write to storage, yeah. Instead, this is what you would want to do. So you need to explicitly rewrite that whatever lives under that key. So that was mapping, right? So mapping and that other like type of working with storage, they're called unpacked layout, just because of the fact that the values do not occupy a single cell in the key value database. And lazy is even more hands or more manual way of defining the storage of your smart contract. It's a bit of a misnomer because lazy, it's not like whatever is lazy is initialized on a first read. It's lazy because when you first read it, you just get a reference. So you do not encode the data. And lazy, it just wraps some type that you define yourself. So some can be a single collection, can be like a struct with different, usually it's a struct with different fields. And you can either define your own key or it will auto-assign one. But it's actually a good idea to define your own. Why we'll talk about later, but it ties into upgradability of smart contracts. And it provides, at that point, it provides parcel access to it, just like a mapping. Here's what it looks like. This is the root storage, right? The moment you read it, it reads that value, decodes all these fields, but when it comes to decoding that particular D field, it just knows it's a pointer to some other place in the storage. And only when you read that, do you pay gas for actually decoding that type. So you can see, yeah, that's why lazy is maybe a bit of a misnomer, because it was already initialized at that point. It's not that it gets initialized then. And that immediately brings us to the upgradable questions. Yeah, good idea.
Yeah, Marisha. Here. So, and the yeah, that's like lazy. So, what's the benefit of using lazy storage actually? Like, okay, we know the execution is kind of like you want the code until you read the value, but then I think it's kind of like you kind of like sacrifice memory reading to less cost on gas for executing, right?
Well, security not really, because everything's public anyway.
Not
but
security, like computing. Like you read many, like you read a lot of entries of storages to kind of get like fast execution and less of, or
yeah, obviously it will be faster, but that's honestly, that wouldn't be my first concern. My concern would be just gas usage. If it's like a large structure, it would just make an unnecessary read all the values that you do not work with. So if you have a contract that has in its storage a bunch of fields, right? And let's say you just read one of them, then why pay for decoding all of them? Because you have to lift all of this, live in that, under that cell. So the moment that you read it, you have to decode all of them. You have to know, is it a boolean, is it an integer, vector, struct, whatever. And if it's packed into the type, you do not pay for that. It just knows, oh, that's a pointer.
also okay. So the benefit of layers is kind of like it will kind of go on decoding only your value, but non-lazy you have to decode all of them to kind of see which one is your value. You have the struct storage value with A, B up to D, and then D it's a pointer to another value, right? To
Yep.
another cell. So one thing is, if your value, for example, it's B U32, it means you have to decode bool U32 and then you get your value. But then if your value is on lazy, it won't decode all the bool and the U32. It won't. It's just go to lazy and consider it a pointer, then go to the cell to decode the value, right? It will skip all the recording.
Yeah, that's correct.
So it's kind of like saves the gas for computation, right? But then you have to read other storage entry.
It's it's an optimization, yes.
Okay, thank
you. You could even, I mean, you could take it a step further. So there's nothing stopping you from storing a mapping under a lazy, right? Why not? Then the moment you read that pointer, it knows there's a mapping, maybe some other fields, maybe a count, for example. And depending on whatever, you could define a logic that you start reading from that mapping whenever the counter is like above some value, some threshold, that type of stuff.
In the previous slide, can you have two fields share the same manual key?
Oh no.
Like, does it just fail to compile, or how does it prevent it?
I mean, if you write two values to the same key, and you just overwrite the value.
But like, what if they have different sizes?
So normally, unless you go around Rust types, like Rust will stop you from that, because there'll be like, if it's a struct, right, and there'll be a different type, so it won't allow you. But the moment you work directly with the key value database that the storage is, and you can do that, you don't check the types. You could put whatever there. You could put whatever bytes. You could break a contract like that. Yeah, sure. Like, it does no type checking. It's just Rust that gives you type safety. There's like in the storage, there's nothing there.
Can you show the previous slide again?
Previous slide.
Yeah, the one that had the manual key. So like, what if you had data 2 and it's like lazy, and then it's like data, like a different data struct, and then does Rust would fail to compile here if you use the same manual key?
Not even Rust, but the
Ink
compiler will catch that. Yeah.
The compiler will catch it.
Yeah. Well fed, carbonated. So just before the lunch break, we were talking about the storage, how things are arranged, what kind of options do you have to control that arrangement. And this is going to tie to this next part of the lecture where we talk about upgradability, upgradable smart contracts. I'm actually going to give a small rant in this place. We quite often, you hear that blockchains or smart contracts, you hear about the term immutable thrown around a lot. I think it's a very unfortunate term that it was coined. Because if something's immutable, right, how can it make progress? How can it move forward? And blockchains, in fact, they are immutable, right? There's this liveness property. If you remember the consensus lectures from the yesterday, they need to make progress all the time, regardless. Like if there's no actions, there's no transactions, they still produce blocks, just empty blocks. And this is what we want. So in fact, we should not be talking about immutability. We should be talking about smart contracts and blockchains which are append only, because you cannot roll back history, but in fact you can keep adding to that history, changing it as it goes. End of rant. And within the life cycle of a smart contract, you're gonna find yourself wanting to add things, remove things, change things quite a lot. And that's where upgradability comes into play. Ink as a language and a smart contract palette and substrate has been built ground up with that in mind. You might know from the Solidity, for example, you might know a proxy pattern, which is a way to go around the fact that the upgradability is not built into the EVM. In Ink, things are a little bit different because of the separation between the contract and between its instance. You can treat the contract address as a pointer to the code that is stored in some other place on chain. And that gives you the possibility to update that pointer, basically make that pointer point into some other code. And that's the OP code for doing that is called set code hash. And here we can see example of doing just that. We have a transaction which takes a mutable reference to the contract, to its storage. We have some 32 byte array, which is the address of some other code. And we, using that OP code, we change what the smart contract's address points to. So we basically update the whole smart contract logic. And this can return, this can fail, or this can result in a success. Just about the only way for this to fail is if there's no storage cell occupying that code hash. There's some important things to remember about when updating your contracts, and that's the fact that these contracts have storage, so there's already going to be some state living living in these cells, and you have to make sure that the new contract code is compatible, right? That it can read and write to this new schema. And this is completely up to you. So here we have an example of that. We have a contract with two fields, an integer and a Boolean value. We have a getter that returns a tuple, so it returns the integer and the Boolean value. And using the setCall hash, we're going to update it to this contract. So we're going to just flip these two values. So the question is, will this work with the definition of the old storage? Like it was defined over here. You know? Mike?
Specifically, the actual contract itself will not work because the actual return value is a tuple of U32 and bool. X is strictly defined here, well, in regards to this function at the very least, as U32. So if you change the type of, well,
so that it's actually.
Oh wait, yeah, I see. I thought, okay, yeah, now I see. Okay.
The only thing I did is I flipped these two in place, but the types.
Yeah, I thought you flipped the types around. I was about to say it wouldn't be compatible, but yes, this would be compatible since X and Y are the same types.
Mm-hmm. Well, normally I would say you're right, but you have to remember that like we just talked. It was before lunch. Obviously.
Oh yeah, yes, that's
well,
true.
we just
yes.
talked about. Where is this?
Yeah, we were talking about the encoding process of the actual skill, basically. So.
So here this comes back. That
yes.
And it's actually worse than that because the moment that your contract, so for example, calls into that reader, for some time you might actually read some bytes from the storage that might make sense, right? It might be able to decode. And it might work for some queries, it might not. So you might not even notice for some time that you have a completely broken state. So this is like potentially one of the worst things that can happen.
Yeah, that would basically more or less just break the contract in specific ways, and more or less, it would depend on the actual variable types, more or less. In this case, it would break, but if it was different variable types, let's say both were U32s, then it would not break if they were both U32s.
But your logic might break, right? Because they would have a completely different semantics. And one would be like age, and the other one would be like balance or something.
That too.
There's a question behind you.
Just to understand, like the public function get values, is that a function of the impl of my contract?
Of both of them. Yeah, it's on a method on
an impl, yeah, on an implementation.
Yeah.
So then like self is basically my contract.
Self is the storage, basically. So the struct, but that's just how inc arranges it, how you would map it to the storage. So this, right, this struct that's defined as storage on which you implement methods. Contract is just like some logic around a storage,
like
how you mutate things in the storage.
If I'm looking at the contract code you gave us at the beginning, like the flipper, for example, then the whatever message, in that case it was from get, then that's part of implementation of flipper, right?
Correct.
And flipper is a struct. So, like, regardless of inc, once you change the code there, once you change the struct, then that won't compile anymore, or like the.
Oh, it will compile. It will compile. That's the problem, right?
Well, how would it compile if like the second?
Types are the same.
Sorry.
Types are the same. It will compile.
What are the same?
Types are the same. So X is a U32, Y is a Boolean, and it's the same in the.
Oh, I see. Okay, it will compile, but just because you changed the order of them, then.
Just because of how codec works.
Yeah.
That's why I would break. So that's the things that you have to remember. There's some other potential breaking changes that you could make. So changing order is one of them. But if I would to introduce a new variable before these two, that'd be the same, right? Because these two change order. So if I read X, it would look into the first field of the struct. It would try to decode it as some other type. If I change the types, right? This would break it as well, but I might actually be lucky because the compiler might change it, but I might catch it.
Just to be clear, the part where it would break would be when it's basically deserializing the contract?
No, not deserializing the contract. When you try to interact with the contract, that's when it would break. And it would reach into the storage.
Yeah.
It would try to decode Boolean.
Yeah, decode, deserialize.
It would read some value, like some byte value that is incompatible. It cannot be decoded as a Boolean. So anything
I
other
should
than
have said
0 or
decode
1.
instead of deserialize, but it's on the decode part.
It's on the decoding, yes.
Yeah.
Yeah, removing variable, same thing, right? There'd be still storage there. It's just that your code would be incompatible with that storage. We had a question?
Yes, one question. If maybe X and Y are both the same type, and eventually someone interchange the swap the places in the structure, this could be something that is compatible, but could do something different than expected or not.
A good example is if you had two unsigned integer values. Just you would have, for example, U8, right, and U16. So some values would fit, and some you'd be not able to decode, even those are two. So that's what I said at the beginning. That might work for some time. It might kind of initially look like it's working, and it would fail in some unexpected ways. Usually, you would just see contract trapped at the end because it would panic.
Okay.
Okay. So here's like what you can do about it, right? If you have a situation in which, right, this doesn't fit fully into the screen, let me make this smaller. Shit. Okay, anyway. Here's the situation. We have a contract, an old contract, it's called A. It has some state, right? So it defines some storage. In this case, just to make things for myself easier, I have wrapped it into lazy, just because lazy allows me some leeway into how I arrange things. So like I said before, lazy, when you read it first, you just read the pointer, and only when you dereference the pointer do you get the actual data that lives under it. And that allows me to be smart about something. So specifically, it allows me to do things like I wasn't able to do before. So for example, to swap fields around in structs, change types, remove variables. And the way to do it is to perform something called migration. And migration is basically like alternating the old state so that it fits the new contract logic. So in that case, I'm changing the types, right? So the first field becomes Boolean, second becomes U32. And I would do that using setcode hash, but in the same transaction, I would call this migrate function. But important thing is that I need to do it in the context of the old code. So I need to migrate, I need to call the new contract code, right? Perform this migration because this knows how to swap these two fields. This is what it does right over here. So it reads that, it explicitly reads from that storage, whatever was stored under that key 1, 2, 3. It decodes that into this old struct, where first field is int, second one is boolean, and I write, like, I flash the state into the storage. So I swap these two fields. I have read them and I swap them, right? So at that point, I'm overriding whatever was under that lazy pointer, right? In one write, I'm updating the value that it points to. The only way, the only thing that allows me to do that is this lazy wrapper on the storage. And one pattern, like that makes it kind of easier, it also allows you to avoid some potentially fatal mistakes, is to pack both of these transactions as one. So basically packing set code hash and a migration and performing them together. And this way, if one of them fails, right, specifically if set code hash would be to go through, but the migration were to fail, you would end up in a kind of a broken state, right? But by putting them together into one transaction, either one of them fails, the whole state is rolled back, and you're kind of good. This might seem kind of obvious, but when we're going to be talking about vulnerabilities, it's kind of important to remember you do not want to leave set code hash like unprotected. So you probably want to introduce some sort of access control, make sure that only a whitelist of callers or some roles can change the code of your contract. Otherwise, it's like fair game.
Yes. Excuse me. So now we have like two states, before migration and after migration, right? And when we read the before migration, after doing the migration, how to know that we need to read it with the older one?
I mean, so the order the things would be, you have the old contract code. You have some storage that's been initialized. It had seen some mutations. There's been some changes to it, but basically you're at the head of the chain and it's in some state, right? There's some values. You upload the new contract code, but at that point, like the state of the storage is still the same, right? It's just like some blob that appeared in some other place. And you need only when you change what your contract instance points to. Only then is like the new logic applies to the old storage, and that's why you want to perform the migration together with changing what it points to.
Sorry, I'm missing a little bit. So sometimes we need to read the previous ones or like replay to know the state of like the initial ones, right? So how will it know that it is integer first and then bool, not the other way around, given that the current logic is only the new?
Well, state is like it's per block. So you mean like if you're reading the history, then
yes, I'm
at
reading
that
the
block
history.
it was in the old state. So that block, the old code was occupying that cell. It does not change history, right?
So we don't need in any way to like sometimes to replay if a new node comes in, it just takes the state as is and does not make sure that they are correct or something.
Once all the nodes, once they've seen and they agreed on that state, this is the head of the chain.
Okay, and if someone reads like the older data? they will read it, the getter will be the new logic, right?
I mean, if someone read, that means he basically replays. And the only way to replace is block by block, and within that block, transaction by transaction, as they happen. So he would arrive, like by replaying that, he would arrive at whatever state was at that point in time. If he keeps replaying that, he would also see the transaction that swaps that updates the contract to point to some new code hash, and so on and so on.
Thank you.
Quickly, if the so this set code, if you go back one, like the set code, the contents of the set code function seems to be like general. Like, so my question is like, isn't it possible to kind of like generalize that as a macro and just, because set code, if this is basically the logic for doing a migration. You set the code and you migrate, right?
Yeah.
So does it not make sense that it would be like just already provided by the platform? So like there would be a macro that would somehow necessitate that you also implement a migrate function. And then
what if you don't need a migration?
Then another macro, but like, yeah.
I mean, but honestly, I can always write a macro, but does it always make sense? Well, I mean, you could.
I don't know. My point in this is trying to understand if this could be different, because the parameters here are code hash, and code hash is the
Just
same.
an address, yeah.
But it's always going to be of that type. Like,
yeah.
And then callback, and like selector is also general. It's like applicable to all, right?
Array?
The callback option selector.
Oh,
I mean, either you migrate or you don't, but like if you do, then you have the option selector.
So callback, right? Callback would be, callback is optional here.
Yeah.
But callback would be, you could pass it here, right?
Whereas actually the callback is not used here, right?
Yeah, here it's not used. It's an option, right? So it's optional. It could be none.
Yeah.
But the way to use it is you could have a implicit contract that whatever you update your other contract to has this migrate function, and it has some selector, right?
Well, so the call migrate, that function, that comes from the framework?
No, you would write that.
So that's somewhere there. And the migrate function?
Call migrate would be basically like some
just
some function that delegates a call to call something with that selector. It's like it's implicit. This is not within the framework. This is like implicit. You would have to have a like discipline, or basically you would have to write that basically.
So the migrate, this is the logic for the migration, right?
Yes, in that case.
Yeah.
So this is completely custom, right?
Yeah.
Because it only makes sense in the context of if the old storage looked like that, and I'm updating it to this, that's what I need to do.
And then call migrate is also a custom function.
Call migrate is just so that I would not bore you with a long boilerplate code. It's just basically it's something that cross calls to another contract, which is stored on chain, but it executes that logic within the context of this old contract.
Okay, so call migrate is a function from the
no, call migrate is a function defined on the old contract, but it calls the new contract. That's delegating a call. It calls the contract, so it basically it's like, think of library, I guess. That it's library has some function, but it's stateless itself, right? because it alters the state of the old contract. And after that, right, you end up with updated logic and updated storage. That's why you pack them together, because if this was to fail and this went through, you would end up in a broken state. It's a pattern, basically.
Okay.
Question on the back?
Yeah, I'm Risha. So the purpose of migrating, okay, so we are changing the structure of the older contract so that the new contract cannot like corrupt the state. So
to be exact,
yeah.
what you're changing is the storage of the old contract.
Okay.
To make sense with respect to the new contract logic.
Oh, okay.
You could have like perfectly innocent updates. For example, you add a function, right? And it's a function that just takes some arguments and makes some changes to the state, or maybe it doesn't even. Maybe it's a pure function. In that case, you don't even need a migration, right? And actually, like from a practical perspective, that's most of the migrations. You rarely need to, fortunately. But this is something like when you need to do it, like test the hell out of it. Make sure, like run it on devnets, testnets. Make sure that, because this is like almost a one-way street. It'd be very hard to roll back from a failed migration. And it's actually, when you're going to be talking about substrate, and its concept of the runtime, a very similar problem applies. That runtime logic and the state of the smart contract are also like kind of need to, they live in a different worlds, but they need to communicate with one another. So a very, very similar concept applies. Question? Mike?
So in order for you to update your code, the first contract should have the set code function.
Yes, correct, obviously.
Okay. And you need to create another contract for the migration code.
Yes.
And then you have to put in the call migrate, which is actually an implementation of how to call that new contract.
It's a detail kind of, so I left it out of here.
Okay, got it.
And the first code had to have the set code function. Does that mean that I also have migrate, call migrate?
So
the functionality, how
this is the old code. I don't know if you see there's like a thin blue line here. So this is the old code, old contract, and everything that's defined on it. This is the new one. So this is still defined in the, because this is just like a boilerplate code. So it's left out.
Okay, so this migrate function, the name is a standard. I cannot change that name. That name has to be there. So yeah.
This?
Yeah. Can I give it a different name?
Of course, yeah. You could call it banana.
Yeah, but then how it calls here? I mean.
Oh, okay. So selector. That's the only thing defining it. So you call a function with that selector. The name kind of binds. If you do not explicitly define a selector, it will be like first 4 bytes, I think, of SHA-256 hash of the name, something like that. If you don't provide it a selector, it will auto-generate one.
Okay, and where is that number coming from?
Where is what?
For the selector number. Selector equal to some number, hex bytes.
That's a definition. That just means selector is.
Oh, that's fixed. 4D4.
Yeah, yeah. It's just what I chose. It's just 4 bytes, like.
Okay, and the new contract doesn't have set code function.
Yeah, presumably below.
Okay, below will be there.
Well, I mean, that's also up to you. You update it to something that's also updatable or not. That's your
Is the
call.
reverse true? So initially the contract was not upgradable, and then we make it upgradable by putting a set code function into it?
No, that'd be hard to do. You need to expose that. You need to expose set code hash. Like it does not put it there, but it should be a very bad idea if it auto-generated code. You wouldn't know about it. It was open for updates.
A question. But the constraint, I mean, the requirement to update the same, the storage structure is that they need to point to the same address zone. And this is specified with manual key. Manual key, in the old state, a manual key in the updated old state, they need to refer to the same address. Okay.
Yes. I could write to a different, I could read something from it, but there might be something, there might be some garbage, there might be nothing there, but this is like a very low, low level way of doing it, but it's explicit and it's kind of safe because you control everything. You control the selector that you control the exact region, the exact region of the key value database.
Yeah, through the get contrast storage and
This gives you like the raw view of the storage of whatever is there under that key. Maybe one more remark. You cannot go like overboard with these migrations, right? Let's say that you have something like a mapping, or you have like a large vector of a lot of values, and you try to build like some large loop. You have to make sure that, because all of this is still gas metered. This is like a normal transaction that you're going to pay for. And specifically, you cannot go over the gas limit for the block. So you have to take that into account as well.
Why do we have to make that message? I mean, publicly callable, we put message only if we have to allow a function to be callable from outside. So this migrate function is declared as message.
It's a message, yes.
But that is called internally. We could go without declaring that message.
Oh. But then you couldn't do a cross-contract call. You would have, then it would have to be, then basically it would have to be compiled into the old contract if it wasn't a message that you can call. It'd be like a different, you would have to basically write your old contract knowing what you're gonna update it to eventually, which is...
So this remains callable after in the upgraded version many times, and this will be basically doing remigrating. I mean,
I'm not sure I follow.
This migrate function remains in the upgraded contract.
Yes.
And this can be called again and again.
Yeah, that's obvious. Yeah, that's a good point. It'd be a good idea to make sure that you can call it only once. Yes.
Okay. Thank you.
It's a good question. Yeah, access control. So there can be many solutions for this. It could be done for a cross-contract call or something simple like that. Make sure that only the admin can do that. Okay, and so this brings us to the next part of this lecture, which is where we're gonna go through some past hacks and like vulnerabilities that you need to watch out when writing smart contracts. This might have already been covered, I guess, because I mean this was a big one, I guess, or a very important one. It had important repercussions. In terms of what happened itself, it's almost like simple, almost by today's standards, but in fact these attacks and these vulnerabilities are still to this day. It happens that that hacks because of this vulnerability that was left in the original DAO contract. So this was like way back in the day. And Ethereum was, we kind of had this blockchain thing, we had smart contracts, and it was still in stage of kind of a killer app. And the DAOs were supposed to be it. So the DAO was the concept of decentralized autonomous organization, kind of like a on-chain VC fund where people could vote with their tokens for a project, and it would give the project like funding. So the idea was great, only that soon after being launched, it has been drained of all the funds. And actually not just drained, but everybody watched it as the funds were like kind of slowly siphoned out of the contract, block by block. And the funds, the original funds, because of the terms of that original DAO contract, they were subject to a 28-day holding period, which meant that there was still some time to kind of try and organize some type of a rescue. And this made news because the contract itself, remember this was like early days, there weren't that many dApps on chain. I think it attracted like close to the fifth of all Ethereum back in the circulation back then. So this was huge. And there was like a committee formed of people discussing the way to try and rescue these funds. And they faced a difficult decision, right? So at that point there was no way to rescue the funds that were already stolen. There was an attempt to basically using the same vulnerability try and siphon the funds and rescue them this way just faster than the original attacker. But obviously the funds that he already got would be stolen, which was already more than 50 million worth of Ether back then, more by now. So the two options left were like, well, we either let it be, let it happen like it's, because it's part of the blockchain history, this and that, decentralized, or we roll back. So basically we create a fork. So we take the history from some block in the past, and all the miners, they start creating blocks from that point on, and we like forget the old history. And that's what they have done. They forked Ethereum with a majority of the votes, but some miners still chose to mine on the old history. And like this created a chain called Ethereum Classic, which actually still exists to this day, has its own updates and miners, and the token is traded. And the exact attack that happened became to know as reentrancy. And it goes something like this. Before we actually see the exact code and where the vulnerability was, we have to talk about something called a fallback function. So Solidity has a special function. Nowadays, you can call it using a fallback keyword, but it's a function which is called when basically no other function matches. Originally, there was only a receive fallback function. It was a function to accept funds. So basically, when you send some funds to an Ethereum contract, that's what this call would be executed. And the problem is, or maybe not the problem, but these fallback functions, they can invoke arbitrarily code. And that's what the attacker used. So this is kind of a reproduction of the DAO contract using Ink. Ink does not have a fallback function, but it's not immune to reentrancy either. So there's in a storage, we have a mapping with balances. So those are like, let's call them investors. And then any investor, he can call into that deposit function, right, and deposit some funds. And this is recorded in the storage. So perfectly innocent, right? Nothing wrong here. And then this is obviously a simplification. Normally there's this, in the original DAO, there's this 28-day holding period. Some other terms applied, but this is basically the gist of it. So the caller can withdraw funds. We read as deposit, right? The contract returns early if he didn't make a deposit. And then we call into another, to withdraw the funds, we call into, so this is like, this mimics this fallback function. We call into another contract, which has a selector. So basically has a function which is payable and accepts funds. So that's basically like a situation in which you would have, after withdrawing, your funds go to some other contract and it holds it for this 28 days, and afterwards you can withdraw them from this other. And record that fact, right? That you have withdrawn from the original DAO contract, you've withdrawn your funds, and call it a day. So can you, maybe already you can spot a problem here. Yep. I think you were first. Yeah. Yeah. And why is that a problem specifically? How would you, maybe read me your phrase. So knowing that, how would you like go about crafting a contract, an attack? You have an idea? Front. Good throw. Good catch.
Yeah, I don't remember the exact details, but it's something about the calling contract terminates before like it errors in some way, and then the balance in this contract does not get updated. So you call again and again and again and again.
Close.
Yeah.
Let's keep going.
All right, I'll take a shot. All right, so in order to actually attack this contract, you would have to more or less have your own contract, more or less just listen in on the actual emitted events for this withdrawal event, and then more or less call the withdrawal event on this contract again, and more or less just be able to withdraw the balance over and over until more or less gas fees exceed the actual transaction, or the actual balance is basically zero. So more or less, you're just, you're more or less just exploiting the fact that your balances is never updated when you're actually going ahead and emitting the actual event from withdrawal, basically.
I mean, I'm not emitting events here, so.
Well.
Closer. I'm going to say closer. We have another one.
Okay.
Yeah, that would probably make it a lot harder to attack the contract. Yeah.
You meant to exploit it, right?
Come again?
You want to know how to exploit this
Yeah,
contract?
that's the question. How would you craft an attack? Like, what would you do?
Well, I would craft like a smart contract that had like a fallback function that was payable, and the idea would be since this contract is going to pay my smart contract before updating the balance, in my fallback function I will call the withdraw function again. So basically, before the balance is updated, I will be constantly calling the withdraw function. I'm not sure like where does that finish, like if I had to put like a limit or if it goes forever until they're
You would have to put a limit because you could exhaust the
gas
limit. Yeah.
Yeah.
You'd have to measure it, but yeah.
How did the DAO hack work then? Did the attacker had a limit and was constantly calling the that function?
It was repeated. I don't know how many he was able to fit in the block, but whatever he did, right? Like in this case, it's yeah, I didn't put it here, but let's say that it costed you 1 ETH to deposit, right? And you could make 10 withdrawals. If you fit that into a block of 20, you make 19 ETH. On every transaction, you make 19 ETH.
Oh yeah, because he had to actually deposit each time he was withdrawing. Okay.
But at that point, like when he had one deposit, he could withdraw to up to whatever many transactions he would fit in the block. Here it is, yeah. So here's how you do it, right? You would craft a contract that starts by depositing some funds, right? So let's say that in this case it's 1A0 because I work at F0. But whatever the terms of the contracts are, so you deposit the minimal value that you can. And right after that, you call a withdrawal, right? And what happens then is, right, you end up here. This executes, this reads your balance, it's 1 at that point, fine. This goes through, right, doesn't throw. And then you're here. And then it calls back into your contract so that the function of that selector over there, I have defined it right there, right? So this matches. I'm here and I call withdraw again. Withdraw, right? I still have balance because balance wasn't updated. This goes through. I'm over here. You see what's going on, right? Again, in the receive, and it keeps like that. You just have to be smart enough, like measure, and do not go over a gas limit for the block. Yeah. But this is the callback, right? You call into a contract with this selector. You call the caller, so the caller is this other contract that has the receive function of that selector. At that point, it's like recursive. It basically never reaches that. It never executes that line.
Just so I understand, like the withdraw function defines that as part of the withdraw process, it also executes a callback, which is in the build call thing, right?
Yes.
And then like the attacker can see this code and he sees this vulnerability, like, hey, there's a callback here, I can exploit it, right?
Yep.
Okay, and then the exploit is?
The exploit is that this reentrancy, because you keep basically coming back, hence the name, you keep coming back to this withdraw function.
So the attack is basically that the callback would be withdraw again?
Again and again, like it never goes here, it starts like, imagine like these instruction set like just growing and growing.
So I see. So basically the issue is that like you shouldn't mutate the state like the lesson learned. Maybe.
I mean, sometimes you have to,
I mean,
right?
yeah, okay. But like in this case, yeah, it's like
don't let the callback happen before you do the thing.
So, yeah. So going off of what he said, basically, I'm just more or less understanding this myself. So the exec input function actually handles more or less going over into that actual receive function on the attacker's contract. And when we go ahead and execute receive on the attacker's contract, we call it back to withdraw. And more or less it gets into this vicious loop of withdrawing more and more until we reach a gas fee or something else happens. We never actually go ahead and update the balance. That's the whole point of the reentrancy exploit.
Yeah, yeah. You don't you don't reach this instruction. So when you re-enter this function, the balance is still there, basically.
Yeah, we only reach up to like exec input, basically. That's where we call our receive function.
Yeah. We have another question.
Mike?
Yeah. Okay. Meanwhile, can I ask?
Does the transferred value, are we transferring from the DAO contract, or can this like virtually make new balances that are not there?
No, no. It's whatever's in a balance. Like you couldn't go over the balance. Because it's not like in this case, right? It transfers the native token of the. It's not like an ERC. It's not a token. It's the native token. So it's like in case of Ethereum, this would be ETH, right? And the contract has only, regardless of what's in its balance, right? Because indeed you would be like kind of printing money out of thin air. There are attacks like that. But in this case, you could only transfer up to, this is an account system, right? In whatever chain, and Substrate in Ethereum. And every account, like whether that's a smart contract, whether that's a user, it has some balance. So it goes up to that balance, right? So you could siphon up to that balance. And
up to that balance of everyone else?
No, of the contract.
Okay, so basically the reentrancy, if I have balance of 10 and do this like recursively 5 times, I will get 50, right?
Who has balance of 10?
If my account, if you go to the attack, I start by adding balance, right?
Yeah.
So if this balance is 10 and then I have my recursive call that does this 5 times, I get 50, correct?
Yes. Minus your costs, right?
What?
You had to deposit, minus your costs. You had to, the cost of the attack was 10.
Yeah. So those 50, this is my question, like, is there a maximum to what the original contract, which is the DAO in this case, have in total, or it's just I can do this forever and like basically virtually have endless money?
No. You could withdraw up to whatever amount of native coin that contract had.
Yeah. Okay. Yeah. Thanks.
You're not like kind of printing money. These balances, I think you're asking because these balances, like contract only has like a cumulative balance, right? This is like an account and it has like some sum, but you don't know who put what. So that DAO had just a storage for that. Correct.
Yeah, so whoever wrote this withdraw function, what was the selector new and this address? Selector address was to do normally.
Selector?
Yes. So this line, whoever wrote the withdraw, what the writer originally expected.
I mean,
included.
It expected, it's just to mimic, right? You would expect that whatever contract you would normally call, so not the contract which was written by the attacker, it would have exactly the same selector.
Okay.
So about the selector, anybody could come and see which selector this contract was using and then make a new contract that's mimicking exactly the same selector? Like I can come and make my own function that
Everything's public on a blockchain.
Yeah, okay, but how come I am able to make a new contract that has the same selector as the previously occupied one?
It's not occupied. Like, this is per contract, right? You could not have two messages with the same selector within one contract, but that's it.
Within one contract, but this was targeting somebody else, and then the attacker came like, okay, let's mimic that somebody else.
Yeah.
That sounds like a major vulnerability to the system. If I can mimic my code.
Not if you just move this here, done, fixed. It's just it's just because ink does not have this fallback function. Normally, you would you just call the caller without the selector, but boils down to the same thing. It would end up into a logic that you as an attacker wanted to.
Okay, but let's say less malicious intent. Let's say I pick up some selector that I like, and then it turns out to be somebody else already picked it, and I disrupt somebody else's contract without ever intending.
I mean, you would, the chance of, you would have to call into that contract, so specifically into that contract's address. Why would you do that just by pure chance?
4 bytes, I can pick anything.
It boils down to the same thing, like whether we are malicious or you just were typing on a keyboard and happen to type a malicious code. Like, on chain, it looks the same. Like.
Then it could be prevented by writing another withdraw function, which is not bad, and giving that selector address.
Come again?
This selector address, if it is so flexible, anyone can write, overwrite, and all. Then to prevent such attack when it is happening, can we write another withdraw function? I mean, any function, good function, with this selector. So
Yeah.
Okay.
Sure. It just tells you, like, basically within this context, it just tells you where to send the value to.
Okay. And one more thing I is not able to understand, that until it reaches the OK state, this function actually do not write anything on the storage. And even when it is recursing, when the stacks are unwinding, then how it is not being checked, that I'm not able to understand.
Oh, it is. I mean, this, you read that from the storage?
Yeah, but this will unwind piece by, I mean,
That's
call
the
by
problem.
call,
It does
call
not
by call.
unwind.
Okay, I'll check with you offline. I think there's a lot to understand.
One last question, hopefully.
Yeah, keep them coming. This happens to this day, so this is actually super important. This is like a 101 of vulnerabilities, and it still happens.
Okay, it's just that, like, we don't understand the syntax yet, I guess, or at least I don't. Line 25, execute input, blah, blah, blah. What are those bytes referring to? Like, yeah, then answer.
Here, this line?
Yeah.
You mean
Those
the
4
selector?
bytes. Yeah.
This is identifier. This is like just to identify the function. These other contracts are you calling? This is like build call using a default environment. The default environment is just basically defines what the account ID is.
Yeah, I was asking about line 25. So those 4 bytes are referring to the withdraw
This is
function?
a selector. This is what function. This basically tells it what function to call. This calls it what address. And if something lives under that address, this doesn't have any arguments or nothing, so it just sends the value. But this could be like, use that selector and send this call data over there, execute that function with that call data.
But like, what, so the person who wrote this code, I guess you, but like, you know, in theory, like the original code, like what are they saying here? Like, so call, so build, like build call is constructing a callback. The caller of this callback is this caller.
The caller is, whoever called an address.
And then call flags, whatever, execute input. means execute the function with this ID or, yeah, but what is it referring to?
At this point, so this is like a low level, does not have, like we've seen previous example, we've seen this, how you would call, you'd have an interface of a different contract, so you have a definition, you know what types are. This is like a low level way of doing that, right?
Okay.
So the only thing that it knows is, I mean, it doesn't know anything, to be honest. Doesn't even know if
So
it
how
will
does it know
execute.
those 4 bytes? That's what.
This is a selector. This is basically, so you have your contracts like has functions, and these functions are identified by unique selectors. The selectors are unique within that other contract. So it tells it to execute that function, not any other, but just specifically
Okay,
this
so in a higher level implementation, you would pass the
That
name.
would basically mean that whoever wrote this contract, he expected that this function, the one identified by that selector, knows what to do with a balance that you're sending to it. Under the terms of the contract, right? I'm omitting, like this was a big contract, I'm omitting a lot of complexity.
So it would basically refer to another function in the same contract. Like when you're saying...
This is a cross contract. This executes...
Cross contract.
Cross contract, yes. This is not even a delegate call. This executes it in the context of this other contract.
So I just want to understand
So,
like, how.
Go. Raise condition.
Whoever has the microphone.
No, sorry, but I guess you understand that for us this code is kind of counterintuitive because in a deposit, perfect, it's very trivial that I'm going to add my current balance. But why? I mean, and I would like that you explain this to us. Why on a withdraw I'm going to execute an external call that I don't know even what is pointing to?
Oh, I mean, for example, I mean, this depends on the DAO, in the terms of the DAO, like the original DAO written in Solidity, right? It had this holding period of 28 days. So you could imagine that, for example, you already remove it from the balance, right? But it goes into that cold storage, whatever. And the other contract knows, like, after withdrawing your funds, under the terms of the DAO, you're no longer talking to this contract, you're talking to this other contract, for example. Or some other situation, right? This could be like, you could have a central contract, for example, that emits events, so you want to do all the other, you want your indexers to listen to just one address, so you emit all the events via cross-contract call to some other address. It just really depends. It depends on the context. You don't look like I made it any clearer.
No, actually, I don't get it. Okay, there is still a hidden code that emits events, but...
No, I'm just, I mean, for the attack, it's kind of oblivious what was supposed to happen over there. Like, this is just the detail, right, of the implementation. Because that's not, whatever that function was supposed to do, it does not matter. Like, the attacker didn't even have to read it. He just had to know that the funds the funds are sent to a function with this selector. In Ethereum, you don't even have to know that much. You just know they are sent to a receive function, a fallback function.
So I want to understand, like, on the same slide. So how do you decide to write the selector for a function, and the code which you have inside the new this hex codes? So I see there's a on that particular function you have the same hash code, joined together, concatenated, right? So is it like, how do you decide these addresses when we write functions for selectors for different functions?
Oh, they are, if you don't assign them explicitly, they're generated.
Sorry?
They are generated, auto-generated for you if you don't assign them specifically.
Auto-generated. Yeah. So, but when you are writing the code, how do you decide? Like, how do
you just define it. Just put 4 bytes, whatever 4 bytes you want. And
okay. It can be any address, I mean,
any 4 bytes.
Any code, right?
4 bytes. That's it.
Okay. Thank you.
Question? Sorry, I'm still on the previous question, actually. You said right now, any 4 bytes. So I still don't understand what prevents me from making a contract with any selector I want and just find other contracts and disturb them.
And that's exactly what happened.
Yeah, but I can still do it. I can do it at will right now. I can go and find other contracts with 4 bytes and just make my own contract with their 4 bytes. Why not?
Yeah. Yes, you could.
Why not everybody's doing it?
I mean, it would be pointless if you can, unless there's some incentive. In this case, it was monetary. But
I don't know. I'm just a troll. I want to disturb the ecosystem. Why not?
good for you. I mean, go ahead.
It's so easy.
Yeah, yeah. There's like, once we go to MEV, there's like very elaborate games that people are playing for profit. So go ahead.
What can
if
I
you can
say?
break
Okay.
something, like, all the power to you.
Sure.
You had more questions, I think? No? Yeah, we already went over that, but that's just a way to fix it, right? Just update the state before cross-contract calling. And in that case, right, you could only re-enter once, and then you would have an updated balance. So this would throw in that place. Another way of fixing that, so that's kind of ink specific, but within the call flags at the level of the call stack, you can disallow re-entrancy to your smart contract. So it basically just puts it basically flushes the state. So once you have entered the contract for the first time, it writes to the state at that point, and then the second time you would re-enter, it would throw there as well. This is like chronically putting things chronologically. I mean, a second probably biggest exploit on the Ethereum. Again, like by today's standards, this is almost silly what happened, but it was very costly back in the day. And this was like this attack was already a little bit more elaborate because it consisted of 2 transactions. So maybe first a word about what the multi-sigs are. Multi-sig wallet is basically a type of wallet where multiple parties need to sign under like a single transaction to withdraw some funds, or deposit for that matter. And they were, I mean, they still are popular for holding like funds for projects, just because it's, I mean, it's public. It's anybody can check what's happening to the funds they deposited. So it has it has like the properties that you would want from the project's building on the blockchain. And there was basically an implementation coming from Parity of a multi-sig wallet. And this specific multi-sig wallet had a library, and all the instances of that wallet were basically using the codes into that library. So that goes back to the fact that EVM does not have this concept of code hash and an instance. So this is like a way to achieve upgradability in the EVM. There's nothing wrong with that per se. It's used to this day. It's called a proxy pattern. And the way that it works is you have a contract that acts as a pointer to a library contract that stores the logic. And every call that you make within that contract is basically done by a delegate call to the library. So basically in the first place of your storage, you just store an address of this library contract that contains the logic. So if you know Java, for example, then this is like kind of like a super call in Java. And delegate call, we probably went over it in some other lectures, but it just delegate call means execute that logic in this library contract within the context of the caller contract. Yeah, so all pretty innocent, right? The only problem was that, or maybe I'm not going to talk about the problem, I'll let you guess what the problem was, but the library contract contained this function. So basically the function to initialize a new instance, thinking in the terms of ink that we just covered, a function to initialize a new instance of a contract, so define some owners, right? A threshold, so how many signatures, let's say that you have, 10 owners, so maybe you require n by 2 plus 1 signatures, and like as a type of safety feature or whatever, a daily limit of withdrawals, right? And this called these two other functions. So in the day limit, it just wrote the day limit to the storage, and in it multi-owned, it wrote, it initialized the array of the addresses and then the threshold for withdrawals. All good. And this is the exact code that was also defined in the library. So that's important. It was defined in the library of the multisig wallet. And exactly, this is like copied. Can you see what happened? Which line was attacked? Maybe you can see it already. I'm going to say that you've seen this. This is also a fallback function. Function with no name, which is payable. So you should recognize this. It should feel familiar. Should. There's no wrong answers. Oh, there are wrong answers. Mike.
This message data length part, what is it referring to? So message value is like this is the amount to be sent, right?
So this is like if
there's
no value is being sent, right? I mean, if there's some value, emit deposit event.
Yeah.
Fine.
Otherwise,
if no data sent,
then
if data sent, delegate a call. If there's some call data, that's what it says.
Yeah. So then, but what is the type of this data? Is it a string?
Yeah, no, this can be anything. This is just a. Okay. Are you close? Are you swimming?
I mean, that already sounds suspicious because then you can just put whatever in the delegate call.
And what? So what do you think? What did the attacker?
Delegate call. You can init a wallet.
You could.
Or like
You could what?
Init a wallet. Because it's multi-owned.
Yeah, so that's exactly what happened. The fact that this was a library, right? It's just context, right? The moment that you called init wallet on the library itself, library is also a contract. It has some storage. It's just not initialized. But the moment that you called it, right? You were able to write whatever owner to it. And at that point, you were pretty much like the owner of the contract. You could execute whatever you wanted. Right?
Question, please. So
the message data, the delegate call message data, are we is the data code here, or like how did we delegate to the multi-owned or the init wallet?
It just matched, right? Like this was false. So he didn't set any value, so this didn't end here, so he ended up here. But he called the init wallet. So if anything else did not match, call init wallet. So he made himself basically like reinitialize the contract. He made himself the owner. So he wrote, he passed call data. So this message data was like his own address, 1 presumably, maybe even 0. Yeah, I don't think he even bothered with a daily, or maybe he set it to some exorbitant amount so that he could. Yeah, I think he did. He could.
So the actual call was wallet library dot init multi-owned. This delegate call is just a placeholder for the init multi-owned, or there is a function that is called delegate call, and it called init multi-owned.
So
you get the question?
Not really.
I am confused about. So now we have a wallet library dot delegate call, right?
Yeah.
This delegate call is the name of the method that we are calling in the library, or it's a
It's
placeholder
just a
for
way
us?
of calling. So you could like forward a call. So you could or you could delegate a call. And then basically, if you forward a call, you say like just call this other contract with all that data and let him handle with that. But if you delegate a call, it says call that contract with the data, but whatever happens inside that logic, this happens in the context of my storage. Question?
Yeah. So my question is on the initializing of the wallet. So if you just pass the data and then the delegate call just init the wallet and he can set the parameters, how did he actually drain the money? Because if you initialize a new wallet, it means even the storage is new, right? It doesn't.
No, you just reinitialized whatever this was writing. So the only variables he had access to, and he needed access to, was the day limit, owners, and how many of the owners are required. So he wrote, I am the owner. Just the threshold is 1, and you can withdraw up to gazillion Ethereum a day.
Okay.
So you could argue, right? There was like multiple vulnerabilities here that, and fixing either one would have probably fixed it, like prevented the hack. But surprisingly, not a long time after that hack, the same multi-sig wallets were attacked again, but this time things were a little bit different because the attacker claims, like to your point, maybe he claims that he has done it purely by mistake. And this time the losses were like almost 500,000 ETH. Only that the funds were locked, and they're actually still locked to this day. This will become clear to you how exactly this happened maybe when we go into the details of the hack. Well, back in the day, I remember this was met rather than with disbelief. A lot of memes were created. So if we go back to the first hack that we talked about, the DAO hack, I talked about how white hat hackers, they tried to use the same reentrancy attack and taking the funds out of the DAO, just trying to do it faster than the original attacker. After that, specifically for situations like that, so like code red, shit hits the fan, we need to act fast. A special OP code was even introduced to the EVM machine. It's called this self-destruct now. It was called like suicide back then. And what it does is it deletes the contract code along with the storage, and all the funds that are there, it sends them to a specified address. So specifically like to clean up and potentially rescue the funds. And funny enough, that's exactly what was the vulnerability in this case. Library contract contained a call like that, which meant that it was available to any other wallet using that library for its logic. And it was protected by the only many owners, like macro, which it basically checks whether this call contains the signature of all the owners of the wallet. So the question is, how was he able to call it? I'll show you this. So this is again the exact code that the library had. So after this first hack, there were two fixes introduced, right? So this code was made internal so that you cannot call it from the outside. And specifically to fix that previous vulnerability, you could call that function in that wallet only once. And it would throw if you didn't. And the way they've done it is by checking, because in the uninitialized Solidity works a little bit differently. So the moment that you create a contract, its storage is initialized. So basically the way to think about it is that if there's a mapping, then it contains every possible value, but initialized to the default value of that type. So number of owners was an integer, so this was 0 in an uninitialized contract. Yeah, so what happened? Can anyone say, do you see it? Sure.
Cool. So this is just a educate guess, I would imagine, but just from evaluation itself, I could probably see some vulnerability with the variable m_num owners. If you could actually modify that to be, 0, if you could actually pretty much avoid the only uninitialized check altogether. That could probably be one exploit, I could imagine.
Yeah, but I mean, the contract was initialized.
So you could probably, well, again, how do you check initialization? It's just by checking the state of m_num owners being greater than 0. So changing that to be 0.
That's close. That's a ballpark. I mean, indeed, it was about the number of owners, but he did not go around that specific check.
Okay.
Yeah, should.
The only many owners, it checks this is a question, not like the answer. Checks the message.data, like in the previous slide. What does the only many owners do exactly? I'm a bit confused
here. It would check, it's like a macro. They would check whether this call is signed by the owner. So it's still the same code, right? you had a threshold of signatures and the owners. So it would check if there was like 10 owners and you required 9 signatures, it would check whether this call was signed by 9 out of 10.
Was it brute forced? But that's really hard. I mean, I'm not sure, but considering this was a library, my guess is he basically deployed his own wallet initially and took ownership of the library that way to then kill it.
Yeah, indeed, he did take ownership of the library, but he didn't even have to. He didn't have to deploy any other contract, just by the fact that library itself is a contract, and it's an uninitialized contract because it was deployed, and kind of like it doesn't have a constructor to be called. So the number of owners on the library itself was 0, right? So this would always pass. Anybody could call like init wallet on the library, and at that point you become like the owner of the library itself, right? And then when you call kill, it kills that library code. So it removes it and all the storage. It transfers the funds to you. In that case, it transfers to 0 because the funds were held in the wallet itself, not in the library. So that's where he messed up a bit. It's like, obviously, like going back to that first, like obviously he was like poking around, trying to troll. Did not fully know what he was doing. I'm speculating, but kind of have good basis to speculate. And he assumed that he probably skimmed through the documentation and assumed that this is somehow, you know what I mean, that he will be able to drain all the wallets. But in fact, this only meant that because this was proxied, right? Because this was proxied, this meant that withdraw or any other function that you would call to, it would try to delegate call, and oh, the library was no longer there, right? So there was no way to withdraw any funds or basically call any other. They're like stuck to this day. And this just, it's just basically very simple to fix, but just always, I mean, like, always make sure to protect like important functions like that. Put a whitelist of people that can call it, whether that's a library, whether that's an actual contract. And I think you can use library contracts, but most of the times you don't have to because of this separation between the instance and the code hash. We're slowly gonna get starting again. So, we finished talking about a longer history of parity wallet hacks. Now we're moving to a broader type of exploit, but these ones are also still happening to this day. Batch overflow exploits, and also as kind of a sister exploit, batch underflow. So the first time we've seen them in the wild was April 2018, where one lucky individual was able to withdraw on the order of 10 to the power 57, which is a big number called octodecillion of a token called Beauty Coin. Of course, there was nowhere near that liquidity for that token, so it's not like there's a richest person in the world working among us. But it was quickly followed by a number of similar exploits, just because the same code was in targeting ERC20 standard. It was like an extension of the ERC20 standard that allowed you to batch multiple transfers. It was like a gas saving, basically. When back when the ERC20s were a thing, so the 2017, 2018. And it got so rampant actually that many of the popular exchanges, like centralized exchanges, like that, like KuCoin, Kraken, Coinbase, they briefly even paused or halted all ERC20 trading before these vulnerabilities were addressed. Yeah, here's a snapshot of that exact transaction. And you can see the rather large number being transferred to one particular address. How did that happen? Well, overflow and underflow, they basically occur whenever CPU, which like computer CPUs, they understand only finite approximations of integers, which are like in mathematical sense they are infinite. So because of how modern CPUs work, they need to be able to put the data in caches, like read it fast. That's why we have types. But at the moment that whatever a given integer, unsigned integer type can hold, whenever it goes above that value, a computer has nothing else to do but to wrap around and come back to basically like in a modular operation, come back to a starting value. So imagine like a clock, right? That once 24 hours has passed, the new day starts. And this is exactly what this one's about. And let's see a reproduction of an exploit like that. Here, purposefully, I'm using a very small integer type to store the balance. But in any other case, it would work exactly the same, you just pass larger values. And imagine that you have a token-like contract and you have this function to basically facilitate sending funds to like multiple accounts at once. Let's go line by line. Let's see what happens. You probably already know what I'm going to ask about. It's where the vulnerability is, if you can spot the problem. But the function accepts a vector of receivers, so the accounts that we're going to send to, and each one of these accounts is going to get some amount of that token. We count them, right? This check is just so that it does not exceed gas block limit, so we limit to 20 account stops. All good. We check who the caller is. We multiply to get like the joint value that's going to be transferred. The caller's balance is, we subtract that from the caller's balance. Blah blah blah. Yeah, subtraction. And then in a loop, we update the balance of all these receivers. So can you see like this one specific line? This one's like kind of easy. There's one line where the problem is. Are you ready? Yeah, why is that? No, the cast is fine. I mean, this is a U size. Cast is gonna be fine. Never goes beyond 20, so which holds into. So U8 is gonna what? 0 to 256.
Yeah.
It's okay.
Okay.
Cast is okay.
So
So maybe the
line is fine. The line is
okay.
It's exactly in that line, in line 16. It's just a different reason.
Okay, so it's
it's line
so
16.
it's not the
yeah.
cast.
It's not the cast. The cast is
So
fine.
the multiplication.
Yeah.
I mean, I was referring to like an overflow. The question is, where is it happening?
Okay, so who said overflow? Why do you think it's overflow? Why that line?
Because like we don't check for a maximum value, and then the value multiplied by the count can exceed the UA.
And in that case, what does the value? Was it? Let's say that. Let's say that I send to 2 accounts and each one gets 128 tokens. So the amount is at that point 0.
Yeah.
Yep. And colors balance. It's not going to be smaller than 0. Fine. Subtract. So even if I didn't have 0, even if I didn't hold any of that token at that point, that's also fine. Nothing wrong with that line. And then all of these accounts are going to get 128 tokens at that point, like basically printed out of thin air. You can actually reproduce that, right? That's kind of like a unit test like reproduction of that problem. I have an account. I have 2 receiving accounts. Both receivers and the sender, they just don't hold that token at all. But after transferring to them, they both have their balance increased just because of that vulnerability. So how would you go about fixing that? Take a look. How could you fix that? Any idea?
Some safety check.
Yeah. How?
Check multiply.
Multiply with? Yeah, you could. So basically, Solidity does have like a safe math library. Rust has all these integer types. They have traits which they have traits implemented on them, which basically they're basically the same code. So you just check whether this does not wrap around.
Like basically, maybe generally speaking, with any arithmetic that we do, we should avoid using like the primitive minus plus whatever, and like use the safe ones. Like
I wouldn't go as far. I mean, just remember that
like
you write a checked, that it's like a checked addition, checked multiplication, but in some cases you would never reach because of some other condition. Like you would never reach. Like for example, there's not enough token in a balance for it to overflow. Also, like it costs gas, right? Because it actually generates all this extra code, and you pay for all these instructions. So that's one thing to keep in mind. So I wouldn't say like always.
No.
But yeah, let's just be careful about it. And in fact, Rust it does have like one foot gun, and that's that. By default, the dev profile and your tests, like for example, your unit test, they're compiled. Dev profile, it does generate overflow checks. So you would get a panic if your addition or some other or multiplication, if it overflows. But in a release mode, it does not, just because it tries to limit the size of the binary. So unless you explicitly define that this is what you want, like either this is where you would put in cargo tumble or directly in a code, you might get some surprises because you might not catch that actually in the unit tests, but in the generated code, that'd be the case. So it really pays to be explicit. And in Solidity, there's a safe math library for all these cases to cover them. So this brings us to this is another part of this lecture about MEV. Specifically, this is a different section, just because MEV and vulnerabilities are not exactly the same thing. Sometimes they are, sometimes they're not. There's not a clear definition of what an attack is, right? What a vulnerability is. But the concept was floated very, very early. So Ethereum was even pre-mainnet. And back then, this existed under the name of minor extractable viruses because we didn't have proof of stake chains back then. And the definition is also pretty broad, but it basically says that MEV is the maximum value a miner. So now that be a block producer, whatever entity is producing the block does not even have to be a validator. But whatever extra monetary value they can extract just by producing a block. And within that block, ordering the transactions, censoring some transactions, maybe even swapping things around, like replacing addresses on a profitable transactions. And after the merge, after the move to POS, and I guess it makes sense also on the other chains, POS chains, this has been, because it's not just miners now that hold this power, like depending on the setup, this can be other entities that are block producers, so we'll see examples of architectures like that. It has been rebranded to maximal extractable value. So we've seen all these examples that we've seen thus far. These are exploits that happen on chain, right? But there's actually another environment which is also a dangerous place to be, and that's the mempool. So mempool is the set of pending, not yet confirmed transactions. So whenever a user, a searcher, or someone creates a transaction and you send it, you do not send it directly to like a block producer, a validator. It enters a mempool. And MEV comes from the fact that in a mempool, everything is public, so everybody can read from that mempool. And when they can read it, they can take advantage of that. So they can, if they see liquidation, for example, it's as easy as copying that transaction, inserting your address instead of the person that found that liquidation opportunity, and resubmitting it only with a higher gas fee for the miner block producer to pick it up and mine it before this other transaction. So basically, someone did all the hard work, searched for it, and just to get it stolen from under him. Which creates, which basically makes a mempool what has been called the dark forest. The term itself, maybe you know these books. There's like a set of novels by Cixin Liu. And the second book in this series revolves around that concept that basically universe is this place where there's multiple competing civilizations, and because the universe is finite, there's so many of them, they hunt one another And this creates a situation where getting detected in this environment is as good as getting wiped out.
Small nerdy correction, the dark forest comes from the Fermi paradox. I think the book is based on that concept that was...
Of
like
Fermi's paradox, yeah.
Yeah, the dark forest is one of the solutions for the Fermi paradox, and this is based on it, I think, but... Yeah.
I'm not sure that Fermi, though, I think that the concept was coined like first in this book.
Like the Fermi paradox presented the paradox, and then other people came up with answers to it, and I think the dark forest is one of them.
Yeah,
But it might be that like this is the answer was defined in this book. I'm not sure.
This is one of hypotheses. But do you know if this was the first time that the concept like did other authors? I know that, for example, Stanislav Lem wrote about a similar concept and some other authors, but I don't know if they called it the dark forest.
Yeah, maybe it could be. Also, fun fact, it's going to be a show on Netflix now.
Yeah,
yeah.
I'll watch. I'll tune in.
Yeah.
If you haven't read, then anyway, highly recommend. And this reference was used in this now famous article by Dan Robinson, Georgios Konstantinopoulos, as early as 2020. So that even predates the DeFi summer of 21, where MEV became like rampant. And in this article, they basically describe like an encounter with one of these apex-like predators, a bot. So the existence of these bots has been, I mean, suspected even before the article that this bot exists, but it's like kind of different to seeing one in action. And the generalized bots, these generalized front-runner bots, are bots that specifically look through mempool for like juicy opportunities. They are able to simulate a transaction. If it's profitable, they just swap their address for their own, and they make sure that it's mined before the original transaction. They can even work with like sets of transactions. If it's like a sandwich opportunity, so there's a front-running transaction, actual transaction, and a back-running transaction. They can detect that. They can even detect like an instruction, the actual instruction within a transaction that generates a profit.
To understand, is the MEV an attack, or it's a way of, like, it's your algorithm of getting the most out of the transactions while mining?
I mean, MEV is MEV. It's kind of like porn. You see and you know. I'm going to say there is no clear definition, right? You could even argue that there's like good MEV and bad MEV. And like, for example, front running, probably bad MEV, drives the cost prices high. Like you get, whereas like if you use DEXs, you get whereas exchange rates, etc. Liquidations, kind of good, right? You want fast liquidation, you want loans to be repaid faster, you want the system to be healthy. Arbitrage, if someone steals your arbitrage, yeah, kind of sad, but again, there's two markets that are imbalanced. Arbitrageurs come, they put the markets in balance. Life is good. So it's a very broad definition. There isn't
So all the things that you mentioned, like, are categorized under MEV.
I mean, if there was there could be an example like someone saw a vulnerability. And it probably happens daily. Someone saw a vulnerability in a smart contract. He submits a transaction to the mempool that exploits that, but the front-running bot sees it, steals it from under him. Was it MEV or was it the exploit? I don't know. Both, I guess.
This is more related to concepts with DeFi, since we already brought that, since we were bringing that up here. Not much to do with MVVs, but we'll see. But why exactly? So for context, this happened a few years back with SBF, more or less, and his ability to more or less make profit for being able to trade bitcoins from the Japanese decentralized exchange, more or less, being able to make an actual profit with that. What exactly happened, and why was that able to occur in the first place? I know it's more so related with decentralized exchanges and whatnot, but I just want to hear why that was possible, more or less.
I guess yeah, you could put that into the definition that MEV happens whenever there's like multiple protocols involved. I guess that'd be maybe a good way to look at it. So there are MEVs like between chains utilizing bridges. You could look for, I mean, you could even algorithmically look for best paths, like Gavin Wood or whatever. But MEV, like back then, at least, when we didn't have that many bridges, or bridges didn't even exist, 2020, I don't think there were any. They were specifically whenever there were like protocols on Ethereum, like DeFi protocols, so 2 or more involved. But I would say that if it's like, I mean, I guess MEV, you could even argue that it happens in like traditional markets, like that Robinhood, famous Robinhood app. I think they were known for sandwiching users. In fact, it was even their business model, to be honest. Many brokers, I guess, still do. It's just not as apparent. It's not in the public. Ah, yeah. I mean, to that point, I think I have a Fermi's paradox on the slide. So going back to that first 2020, Dan Robinson, Georgios Konstantopoulos article, there are 2 researchers, so they're kind of active in like support channels of many of these protocols, especially back then Uniswap, and still is to this day. It's a big DEX. And one of the users has erroneously sent his funds, like instead of the pool, to the liquidity pool token contract. And he was asking whether it's possible to retrieve them. So I guess initial answer was no, they're stuck. But in fact, after thinking about it for a while, one of these researchers came to the realization that actually anybody could retrieve them. In fact, even someone that would be retrieving liquidity would get these extra tokens. So this was kind of a ticking time bomb. So the rescue would be easy, right? You just call this burn function, you get these tokens, and you return them, or even the original person that had the problem could do it. The only problem was that the moment that you submit this opportunity, someone would like front run it in a matter of seconds. And they were fully aware because of this article written a year before that speculated the existence of these generalized front runners scanning the mempool. So they had to design a way of obfuscating that burn transaction and like rescue these funds without alerting the bots. This is what they came up with. So they created 2 contracts. So a setter contract. A setter was like a super simple contract with one admin kind of like address. And it would kind of like turn on this only address. So the owner of this setter contract was the only one that could initialize the getter. And then the getter would be the contract. So the setter calls this set function because it's the only address that can do that. At that point, it's on. If not, then this transaction reverts. But if it's on, right, call that burn function with the destination that's set in the constructor. So basically, the idea was that split that into two contracts that have to be executed one after another, and bury that burn call like inside of the bigger transaction, with the hope that before the front runner executes all these transactions and finds that burn that actually rescues the fund, this is already like part of history. This is already mined by someone. But there's a problem, small problem here with this setup. Maybe you can see it already. It's actually not. It's not a vulnerability per se. It's just more like a challenge, that you really need to be careful how you use these contracts. Time is of the essence in that case. Can you see it? Well, basically the problem is that you really need to be careful, make sure that set, right? There's 12 seconds between blocks in Ethereum. So you need to make sure that set and get, they're mined at least in the same block, right? You really do not give time for this get transaction to linger in a mempool because someone would notice. And unfortunately, that's exactly what happened. Like during to the pressure of time or something, they let this other transaction slip. The set was in an earlier block, get was in a later block, and someone just swapped the funds. Yeah, so maybe you have this is like a general question. Let's say that you are a searcher, arbitrager, maybe you look for these MEV opportunities. What could you do differently? Completely differently. Not even talking about the code. What could you do to make sure to get your transaction like mined? What would you do differently? Like, if you're a MEV searcher, what would you do to make sure that your transaction is, someone doesn't steal your transaction from under you? You do all this hard work, you want to reap the rewards, what do you do?
Have one function instead of set and get, like have like instead of two functions, have one function that's set and get. So it sets it and then returns the.
Yeah, but then the bot just runs it, simulates it, and sees that it gets funds at the end of it, so he just steals this transaction.
Maybe like burning the funds to the smart contract that was the setter, so the front runner will have to like deploy a similar smart contract because
I mean, you could potentially obfuscate it a little bit better if this was like a no-op, right? Because let's say these generalized front runners, they look at the instruction level. They don't even look at the whole transaction. So maybe you could like, make it if it's not on, or if you're not the, because obviously he didn't steal the whole transaction, he just stole that one because he was not he didn't even call that contract, right? He just copied the copied the call data. If you made it no op, maybe when simulating it, he would like, you could have like an instruction that says, if sender is not together, just do nothing. Maybe you wouldn't spot it. Maybe that would fix it, but probably not. Like the thing to do is just avoid mempool altogether. Just contract with a miner, give him your transaction to include in a block when it's his time to mine a block. For some extra fee, he mines it, and you skip the mempool altogether. And there's offerings like that. We're gonna talk about it later. Why this is not a good route to go, and specifically why MEV has to be addressed somehow. But for now, I'm gonna leave it at that. Like in Fura node, they just
like in the context of the code we saw before.
So this, I mean, mempool is not part of blockchain, right? Mempool is just a queue of pending transactions. So if you go to Subscan, Etherscan, you can see a list of transactions that are pending, waiting to be included.
So what do you mean here, avoid public infrastructure? Like what is it referring to? I just don't understand.
I mean, avoid like miners that that are part of it. Like for example, avoid Infura nodes, avoid what are the other offering. MetaMask is a good example. I think they mine transactions themselves as well.
I can't hear you.
MetaMask, just contract completely off-chain contract with some miners that offer private pool. So this is the way this works is you have, if we're talking POW, right? Someone finds a hash, and at that point in time, he's eligible to propose a block. So he chooses transactions, right? Until he fills the size of the block. And naturally, he chooses the transaction, he or she chooses the transaction that offer the biggest tip for them. So biggest gas fee. But if you transact off-chain, then potentially for maybe for a percentage of that opportunity you've found, you can pay that to a miner, and your transaction is never visible to the public. Just when it's his time, he takes it and he includes it as part of the block. Then the block is mined.
So by public infrastructure, you're referring to the mempool, in this case?
Yeah.
Okay.
You refer to what, sorry?
Mempool.
And the private, like I didn't really understand. So mempool is the queue that all the nodes has to have the transaction and mine the block, or like decide on the block.
Yeah.
What are the block like X-root and like the what do we mean by private pool transaction exactly?
There's just miners that you can contact with, and it's the core of their, or it's one of their businesses to. They controlled a lot of hash rate. Let's say that they control 40%. Collectively, they control 40% of the hash rate, right?
Okay.
So as long as your opportunity is like, let's say, twice as long, the MEV that you found.
So I send my transaction specifically to one of the pools to be private.
You have to have a business relationship with them.
Okay, not anyone can just send. Okay. There is a question there.
Yeah. So, is this issue prevalent in any network that has public transaction pools or mempools, or is it mostly like Ethereum? Like, for example, is within Polkadot, is this also a problem, or are there certain things that prevent this?
Yeah, it's it's always a problem. Like it doesn't matter if it's a POW or POS chain.
Thank you.
I'm gonna run a little faster. I'm just wanted to talk about this one. So why exactly is MEV a problem? Why does it need to be addressed? Why do we have to do something? So if it goes untreated, there's a couple of problems that it causes. First one is gas price inflation, right? So all these bots, they have it in their mempool. One bot stealing from the other. So, you know, one bot, like let's say you're a searcher, you submit a transaction, you put a gas fee of X, and another bot tries to steal, you put 2X, another, he puts 3X, and this is like really automated these days. So they have these battles, and this drives gas prices higher and higher, which hurts the usability, obviously. There's a lot of transactions that are getting stuck in this mempool because of these bots battling. So I just wanted to buy this NFT, you know, the kitty, but you have to wait a long time. Another problem is that this is a slide from Flashbots. Flashbots is like a company, entity, non-profit that researches MEV, creates products, and they track MEV. So pre-merge, post-merge, almost $1 billion worth of MEV. And yeah, blockchain being a zero-sum game, if someone won 1 billion, someone had to lose it, right? And the problem is that I lose, you lose, he loses, she loses, right? It's the regular users, like the end users of the chain that this value is transacted from, and higher gas fees, and worse like exchange rates, etc. But there's even a worse problem than that, and it's that MEV, at least in the longest chain context, it can destabilize consensus. And why is that? Assume that there's, you know, there's a block, there's another block that had these three juicy MEV opportunities, like liquidations or something, and this block is already part of the history, another block has been mined on top of it. So now, there's a miner that sees that. This is what he does. And remember, the miners are supposed to mine on the longest chain, right? So he should start creating another block over here. Instead, he takes this block, he inserts one of these transactions here, but he kind of leaves out these two other transactions for the other miners to take. And these other miners, well, because they're rational players, they want to maximize their profit. Why would they mine over there, right? The only thing they can win over there is the rewards for creating a block. But there's these juicy MEV opportunities. So they start mining here, right? And they cause a reorg. Another problem are these private mempools, right? They cause a horrible concentration of power. So because it's basically like the rich get richer type of problem. So you already have mempools. You already have miners that control a large amount of hash rate, or even have like a large stake. Doesn't matter. And it's very hard, and it progressively harder to basically become another block proposer in that setup. Just because everybody, you know, these opportunities, they don't live forever. Once you find one, you want to beat others to it. This is a race, right? You want to beat others to it, you want to reap the rewards. So you would contract with someone who holds a vast amount of the hash rate to maximize the chance of inclusion. So Flashbots, like I said, is a company that has a couple of products that try to cure that problem. I'm gonna specifically talk about one called MEV Boost. MEV Boost is one of, there's multiple implementations, one of the implementations of the concept called proposal builder separation. And that's the way that it works. But it's split, so because these validators, right, or miners, validators, they have the most power because they're the ones that propose a block, so they can reorder transactions within the block. Instead, we take that power away from them and we put it in the hands of these entities called block builders. So these searchers, right, all the users that send transactions to their mempool, these searchers, they work with bundles. So they, for example, if it's like a sandwich operation, there's going to be 3 transactions. There has to, the ordering matters. So that's what they're interested in. They're interested in having all these 3 executed in exactly that order. They contract with these block builders. They send the bundles to them. These block builders, they build the blocks of them. So they basically select the ones that have the most fees in them. And they send them to these entities called the relayers. Relayers, in turn, they talk to validators, or the block producers, right? But they don't send them, they don't just send them blocks. They send them blocks and they wait. But they don't send them blocks, I mean, because at that point, if they would send them the block would just, the validator would just look at this MEV opportunity, would steal them, would submit them on his own. They send commitments to a block hashes basically. And validators, they sign them. They send the signed blocks to the relayers, who send them to the blockchain, at which point that's part of the history. So yeah, many problems with this, or actually not problems, but let's think for a moment what happens if the block builders cheat. Can they cheat here? Can they steal from MEV searchers? Yeah, they can, but just once, right? Because you wouldn't trust someone crossed you once, you wouldn't trust them. Relayers, same thing, right? If they steal from the block builder, you could do it only once, you would never transact with them again. And same for the validators. So it kind of created this circle of game economic type of trust in a rent for space type of agreement. If you want to know more, I can highly recommend DeFi Mock lectures, especially the ones by Arthur Gervais. He's like a researcher in the MEV space, DeFi space. Dan Bonnet lectures as well. He gives like a cryptographer view of MEV. This Bankless podcast, there's a couple episodes about MEV specifically, but this one's good. And Flashbots has a web page where they quantify MEV. They have products. They have like a dashboards updated daily. Yeah. So that's going to be the end of this part of the lecture. Piotr's going to take over unless there's, of course, questions to that last part. But basically, I wanted to end that if you're writing smart contracts, there's a couple things to take into account. So remember about all these basic vulnerabilities. There's now tools that can, automated tools that can test for them, but get them audited nonetheless. Think not just about the vulnerability in your contract, but also about how MEV comes into play. There's like simple ways to protect or at least make it harder to front run or background the contracts. So especially if it's like if it's a DeFi protocol, take that into account. Yep. Questions?
Yeah,
on the slide where consensus problem was there because of private mempool, if the mempools are kept private, then how it goes? So really, consensus won't be able to reach because one node is including some transaction which is not known to other nodes, and they will see the block as different. So consensus will be hard to reach. So am I understanding correct? That's the problem?
No, the problem is that the incentives changed for the validators. They're supposed to be incentivized to be like to keep honestly building on the longest chain, which means take the last block and build on that. But here, the problem is that the rewards from the math, they're larger than whatever they can get by being honest. They're actually not honest. They are their incentives are completely monetary. Like you assume, right, in the longest chain, at least context, you assume 51% majority is honest. But it's not necessarily the case. Here it's not the case, right? That's the problem.
And in case of Polkadot-like system where finality is there and almost after every block it is finalized, this problem shouldn't be there. I mean, this opportunity shouldn't be there.
Is grandpa longest chain? Yeah. It'd be a problem. It doesn't matter if it's a proof of work or it's a proof of stake. As long as there's, as long as the reorgs are possible, because everybody mines on the longest chain, the problem exists there.
So if things are proper, grandpa really finalizes in one block time. So very quickly blocks are being finalized. It doesn't take a long time. So.
Not sure. It doesn't the block time doesn't matter here.